Hello there, and welcome to Science for Sleep, where curiosity slows its steps, science speaks softly, and the universe becomes a quiet place to rest your thoughts. I'm glad you found your way here tonight, whether you're settling into bed, leaning back in a chair, or simply giving yourself a moment away from the rush of the day. There's no hurry here, no countdown, no need to keep track of anything at all. Just a gentle journey through ideas that are big enough to make everyday worries feel a little smaller. Tonight we're drifting toward a question that starts with something simple and grows into something vast. A question about size, distance, and what it really means to be large in a universe that already feels impossibly wide. Somewhere out there, far beyond the familiar dots of stars we see from our windows or city streets, are worlds that stretch the limits of what we call a planet. Some of them are so big that even our own giant neighbours like Jupiter begin to seem modest by comparison. So, instead of rushing to an answer, let's ease into the idea together. Let's wander through what it means to search for the largest planet ever discovered, and why that search feels a little like standing at the edge of the ocean and wondering where the water truly ends. Before we go any further, I'd love to know something simple and human. Where are you listening from tonight? Are you tucked away in a quiet bedroom, on a late train, or perhaps under a blanket with a soft glow from a screen nearby? And what time is it for you right now, in your small and personal corner of this very large universe? It's always a comforting thought that while we're talking about distant worlds and enormous planets, we're also sharing this gentle moment across many different places, all connected by the same slow turning of the Earth. If this calm little expedition turns out to be a pleasant part of your evening, if it helps you relax or sparks a bit of quiet curiosity, you're always welcome to show a little support by liking the video or subscribing. It helps this space reach other listeners who might be looking for the same kind of peaceful pause. There's no pressure, of course. Just consider it a friendly wave across the cosmic distance. Now, let's begin with something familiar. Close your eyes for a moment if you'd like, and picture our own solar system. The warm glow of the sun at the centre, the rocky inner planets circling close by, and then, farther out, the giants. Jupiter, with its wide stripes and swirling storms. Saturn, with its thin, elegant rings. These worlds already feel enormous compared to Earth. If you could place Earth next to Jupiter, it would look like a small marble beside a beach ball. Jupiter is so large that more than 1,000 Earths could fit inside it. That alone sounds impressive enough to win a cosmic size contest. And yet, in the wider universe, Jupiter turns out to be more of a starting point than a final answer. The night sky we see is only a tiny slice of what's really out there. For most of human history, every star we looked at was just that, a point of light, distant and unreachable. It wasn't until fairly recently on the scale of history that we realised many of those stars are not alone. They have planets of their own, circling them quietly, just as our planets circle the sun. These distant worlds are called exoplanets, and discovering them has become one of the most exciting parts of modern astronomy. The first confirmed discovery of an exoplanet around a sun-like star happened in 1995. That might sound like a long time ago, but in scientific terms it's very recent. Since then, astronomers have found thousands more. Some are small and rocky, like Earth. Some are frozen and distant from their stars. Others are so close to their suns that their atmospheres are being blown away by heat and radiation. And then there are the giants, the ones that make Jupiter look like it didn't quite live up to its full potential. But here's where things get interesting. When we talk about the largest planet, what do we actually mean? Are we talking about the one with the biggest mass, the most material packed into it, or the one with the largest diameter, the widest stretch from one side to the other? Because in space, those two things don't always line up the way you might expect. Imagine two balloons. One is filled tightly with air, firm and heavy. The other is much larger, but only lightly filled, puffy and soft. The second one takes up more space, but the first one might actually weigh more. Planets can behave in a similar way. Some of the largest looking planets, the ones that stretch out wide in space, aren't necessarily the most massive. They're often made mostly of gas, and their material can be spread out in a kind of swollen, expanded state. This means the search for the largest planet becomes a bit like asking whether you care more about height or weight when deciding who is the biggest person in a room. Astronomers usually focus on size in terms of radius or diameter, how wide the planet is, because that's something they can often measure more directly when a planet passes in front of its star and blocks a bit of the light. That method, called the transit method, has become one of the main ways we discover and study exoplanets. When a planet moves across the face of its star from our point of view, the star's brightness dips slightly. By carefully measuring how much light is blocked and for how long, scientists can estimate how big the planet is. It's a delicate measurement, often involving changes in brightness smaller than 1%, but with modern telescopes and patient observation, it works remarkably well. As this technique improved, astronomers began to notice something strange. Some of the giant planets they were finding were far larger than anything in our own solar system. These weren't just Jupiter-sized worlds. They were Jupiter turned up to 11. Many of these enormous planets orbit extremely close to their stars, much closer than Mercury is to the Sun. Because of that, they are incredibly hot, with temperatures that can reach thousands of degrees. The heat causes their atmospheres to expand, making them puff up like overheated balloons. These planets are often called hot Jupiters, and they are some of the largest looking worlds ever observed. One of the early surprises was a planet called HD 2009-458b. It was one of the first exoplanets observed passing in front of its star, and it turned out to be larger than Jupiter, even though it had a similar mass. That alone was enough to make scientists rethink how giant planets behave under extreme conditions. As more data came in, the list of oversized planets grew. Some had diameters nearly twice that of Jupiter. To put that into perspective, if you placed one of these planets where Jupiter is in our solar system, it would stretch so wide that it would start to encroach on the orbits of other planets. It would dominate the space around it in a way that feels almost theatrical. But even that wasn't the end of the story. One of the current record holders for sheer size is a planet known as WASP 17b. This world has a radius nearly 2 times that of Jupiter, making it one of the largest planets ever discovered by diameter, and yet its mass is much lower than Jupiter's. It's a giant but a very light one, at least by planetary standards. Its atmosphere is so expanded that it has been described as one of the puffiest planets known. WASP 17b orbits its star at a close distance, completing a full trip around it in just a few days. The intense heat from the star causes its outer layers to swell, creating a planet that looks enormous when measured by size alone. It's a world that seems to blur the line between a planet and something more like a drifting cloud held together by gravity. Then there's HAT P67b, another planet that challenges our sense of scale. This one is even less dense, with a size that makes it one of the most inflated planets ever observed. If you could somehow stand on a solid surface inside it, which is very unlikely since it's mostly gas, you'd find that the gravity feels surprisingly gentle for such a large world. It's a strange thought, that a planet can be so big and yet so light, relatively speaking. But here's another twist. There is a limit to how large a planet can get before it stops being a planet at all. As a giant planet gathers more and more material, especially hydrogen and helium, its gravity increases. At a certain point, the pressure and temperature in its core become so intense that it can start to fuse hydrogen, even if only briefly or weakly. When that happens, the object crosses a line and becomes something else, often called a brown dwarf. Brown dwarfs are sometimes described as failed stars, not quite massive enough to shine like true stars, but too massive to fit comfortably into the category of planets. So when astronomers search for the largest planet, they're also carefully watching this boundary. They're looking for worlds that push right up against the edge of becoming something more, without quite crossing over. This makes the title of largest planet ever discovered a moving target. As telescopes get better and surveys become more detailed, new candidates appear. Some are enormous, but turn out to be too massive and get reclassified as brown dwarfs. Others stay within the planetary range and claim a spot near the top of the size list. What's especially interesting is how these discoveries change the way we think about our own place in the universe. For a long time, our solar system felt like a kind of template. Rocky planets near the sun, gas giants farther out, everything in neat, predictable orbits. But the giant planets found around other stars often break these patterns. They're close to their stars, tilted at odd angles, or moving in ways that don't quite match what we see at home. The universe, it turns out, is much more creative with its planets than we once imagined. As you sit here, listening to this, it's worth pausing to consider how strange and wonderful it is that we can even have this conversation. That light from a distant star can travel across space for hundreds or thousands of years, reach a telescope on Earth, and be turned into a tiny dip on a graph that tells us a planet exists. And from that small signal, we can begin to picture a world so large that it makes our biggest planetary neighbour seem like a warm-up act. There's something quietly humbling about that. Not in a dramatic, overwhelming way, but in a gentle sense of perspective. The room you're in, the building, the city, the planet beneath your feet, all of it exists in a universe where largest can mean something far beyond what our everyday language was designed to handle. And yet, here we are, comfortably human, thinking about it anyway. There's something about the word big that feels simple on the surface, and yet quietly complicated the longer you sit with it. In everyday life, big usually means obvious. A tall building, a wide river, a large dog that takes up most of the couch. We don't need special instruments or careful definitions to agree on what counts as bigger than something else. But once you lift that idea out of kitchens and city streets and place it into the universe, the meaning starts to stretch in unexpected ways. Out there, beyond the thin shell of air around Earth, size isn't just a matter of comparison. It becomes a clue, a hint, a kind of fingerprint left behind by the way a world formed, moved, and changed over time. So when astronomers talk about the largest planets ever discovered, they aren't only making a list for the sake of curiosity, they're trying to understand what those enormous worlds can tell us about how the universe builds things in the first place. Let's ease into this with something familiar. Think about the planets you learned about in school. Mercury, Venus, Earth, Mars, then the giants farther out, Jupiter, Saturn, Uranus, Neptune. Even in that small lineup, size already tells a story. The inner planets are small, rocky, dense. The outer ones are huge, made mostly of gas and ice, wrapped in thick atmospheres. That pattern isn't random. It's tied to how the solar system formed from a disk of dust and gas swirling around the young sun billions of years ago. Close to the sun, it was too hot for light gases like hydrogen and helium to stick around. They were pushed away by heat and solar wind. Only heavier materials like rock and metal could clump together and form planets. Farther out, where things were cooler, those light gases could settle and gather, allowing giant planets to grow quickly and become massive, puffy worlds. So even in our own cosmic backyard, big already points to temperature, distance, and timing. Jupiter didn't just happen to be large. It became large because of where it formed and what was available to it at the right moment in the solar system's early life. Now, take that idea and expand it to the entire galaxy, and beyond that, to the countless galaxies scattered across the observable universe. Each star system is its own experiment. Different sizes of stars, different amounts of material, different environments, different histories. The planets that form around them reflect all of those factors. When astronomers find a planet that's far bigger than anything we see at home, it's like finding a sentence in a book that doesn't quite follow the grammar you thought you understood. It makes you stop and ask what rules you might be missing. One of the first reasons size matters is gravity. The more massive a planet is, the stronger its gravitational pull. That pull shapes everything around it. It influences the orbits of nearby planets. It can capture moons, dust, and even comets. In some systems, a giant planet acts like a cosmic bouncer, flinging smaller objects away or redirecting them into safer paths. In others, it can send them hurtling inward toward the star. There's a growing body of research suggesting that Jupiter played a role in shaping the history of life on Earth, not by being gentle, but by being large. Its gravity likely helped reduce the number of dangerous impacts Earth experienced over long periods of time by pulling in or deflecting comets and asteroids. It didn't make Earth completely safe, as the dinosaurs can testify, but it may have made the environment more stable than it otherwise would have been. So when scientists find planets even larger than Jupiter, they start wondering what role those giants play in their own systems. Do they protect smaller, potentially habitable worlds? Or do they make things more chaotic by disturbing orbits and sending debris flying in all directions? That question alone is enough to make bigger than big feel like more than a fun fact. It becomes part of the search for places where life might exist. Another layer to this is how planets grow in the first place. There are two main ideas about how giant planets form. One is called core accretion. In this model, a solid core forms first from rock and ice, and once it gets big enough, it starts pulling in gas from the surrounding disk. Over time, that gas builds up into a massive atmosphere, creating a gas giant. The other idea is called disk instability. Here, instead of slowly building up from a core, parts of the disk of gas and dust around a young star collapse directly under their own gravity, forming a giant planet very quickly. Both processes can make large planets, but they tend to produce worlds with different properties. A planet that formed through core accretion might have a heavier core and a more layered structure. One that formed through disk instability might be more evenly mixed, more like a giant ball of gas with less of a solid centre. So when astronomers measure the size, mass, and composition of a very large planet, they're not just filling in a catalogue. They're trying to work backward. They're asking how this world came to be, and what that says about the environment it formed in. Size also affects what a planet looks like over time. A very large planet can hold onto its atmosphere more easily. Gravity makes it harder for gas to escape into space. That means giant planets can keep thick, extended atmospheres for billions of years, even if they're close to their stars and exposed to intense radiation. But there's a balance here. If a planet gets too close to its star, the heat can cause its atmosphere to expand and slowly leak away, even if the planet is massive. This creates a strange situation where a planet can look very large because its atmosphere is swollen, but at the same time it's actually losing material into space. Some of the largest looking planets discovered so far are in this category. They're not just big, they're actively changing, shedding parts of themselves into the surrounding space like slow, invisible winds. That process can leave behind a trail of gas that stretches for thousands or even millions of kilometers. In that sense, bigger than big isn't always a stable state. It can be a phase in a planet's life, a moment in time when it's at its most inflated before it gradually shrinks or transforms. There's also the question of how size relates to temperature. Large planets, especially those close to their stars, can be incredibly hot. Some of them have daytime temperatures that rival or exceed those of small stars. Their atmospheres can glow, not from nuclear fusion, but from sheer heat. That creates environments unlike anything we see in our solar system. Instead of clouds made of water or ammonia, some of these worlds may have clouds made of vaporized metals or glass-like particles. Rain on such a planet wouldn't be water falling gently from the sky. It might be molten droplets of iron or silicates, falling through an atmosphere that feels more like a furnace than a sky. When scientists talk about these planets, their size becomes part of a much bigger picture. It's not just about how wide they are, it's about what kinds of physical and chemical processes can happen in a place with that much mass, that much gravity, and that much energy. Another reason size matters is how it affects our ability to detect and study these distant worlds. Larger planets are easier to find. When a big planet passes in front of a star, it blocks more light, creating a more noticeable dip in brightness. When it tugs on a star through gravity, it causes a larger wobble that's easier to measure. This means that for a long time, our view of the universe's planets was biased toward the big ones. We found the giants first because they announced themselves more clearly. Smaller, Earth-like worlds were harder to detect and took more sensitive instruments and longer observation times to uncover. So when we talk about the largest planets ever discovered, we're also talking about the limits of our technology and the path our discoveries have taken. The giants were our first teachers in the study of exoplanets. They showed us that planets could exist in places and forms we never expected. Over time, as our tools improve, we've started to fill in the smaller end of the scale, but the big ones still hold a special place because they often sit at the extremes. They push against the boundaries of what we call a planet, what we call a star, and what we think is possible in between. There's a subtle philosophical angle here too. Humans have always been drawn to extremes. The tallest mountain, the deepest ocean, the hottest place on Earth. The largest planet in the universe fits neatly into that pattern. It's a way of mapping the edges of reality, of finding the points where our familiar categories start to blur. And those blurred lines are often where the most interesting questions live. For example, consider the boundary between a giant planet and a brown dwarf. Brown dwarfs are objects that are more massive than planets, but not massive enough to sustain long-term hydrogen fusion like true stars. They sit in a kind of middle ground. They can glow faintly from the heat of their formation and from brief periods of fusion of heavier forms of hydrogen, but they never fully ignite like stars do. The difference between a very large planet and a very small brown dwarf can be subtle. It's not always obvious just by looking at size or even mass. Astronomers often have to consider how the object formed to decide which category it belongs in. Did it form in a disk around a star like a planet, or did it collapse directly from a cloud of gas like a star? So when a planet gets bigger than big, it starts to challenge not just our measurements, but our definitions. It forces us to ask what a planet really is. There's also a cultural side to this. The idea that there might be a largest planet ever taps into a long tradition of looking up and wondering how far things go. Is there a biggest star, a farthest galaxy, a most massive black hole? Each of those questions reflects a desire to understand the scale of the universe and our place within it. And every time we think we've found an answer, the universe tends to respond with something even larger, farther, or more extreme. From a more practical perspective, studying very large planets can help refine our models of physics. The conditions inside a giant planet are extreme. Pressures can be millions of times greater than what we experience on Earth. Temperatures can reach thousands of degrees. Materials behave in ways that can't be easily replicated in laboratories. By observing how these planets behave, how they interact with their stars, how their atmospheres move and change, scientists can test theories about how matter and energy work under conditions that push the limits of what we understand. In that way, these distant giants become natural laboratories. They're places where the universe is running experiments we could never set up ourselves. It's also worth noting that size doesn't always mean dominance in a simple, dramatic way. A very large planet can be surprisingly delicate in some respects. Its extended atmosphere can be sensitive to changes in the star's activity. A burst of radiation from a stellar flare can heat the upper layers and increase the rate at which gas escapes into space. Over long periods of time, this can significantly alter the planet's appearance and even its classification. A world that starts as a swollen, oversized giant might slowly shrink as it loses atmosphere, eventually becoming something smaller and denser. So big can be a temporary state, a snapshot in a long, slow process of change that unfolds over millions or billions of years. There's something quietly comforting in that idea. Even the largest planets in the universe are not fixed monuments. They grow, change, and evolve, just like everything else. As you let these thoughts drift through your mind, you might notice how the idea of size begins to feel less like a competition and more like a story. Each giant planet is a chapter in the broader narrative of how stars and worlds come into being, how they interact, and how they transform over time. The universe isn't just filled with big things for the sake of being impressive. Those big things are there because of specific conditions, specific histories, and specific chains of events that played out in clouds of gas and dust long before any telescope was pointed in their direction. So when we ask why bigger than big matters, the answer isn't just about finding the winner of a cosmic contest. It's about using these enormous worlds as signposts. They point back to the environments they formed in. They hint at the forces that shaped them. They help us test our ideas about what planets can be and how far those ideas can stretch before they need to be rewritten. If size can be measured in different ways, if mass and diameter don't always agree, and if the line between planet and something else can blur, then what exactly are we counting when we talk about the largest planet? When we use the word largest in everyday life, it usually feels straightforward. The largest slice of cake, the largest suitcase at the airport, the largest building on the street. We look, we compare, and the answer presents itself without much debate. But once that word is carried out into space, into the quiet, distant realm of planets and stars, it begins to behave very differently. It becomes less of a label and more of a conversation. A question that opens into several other questions, each one gently pulling us deeper into how we understand the universe. So let's slow down and sit with it for a moment. When we ask about the largest planet ever discovered, what are we actually asking? Are we talking about the one that weighs the most, the one that takes up the most space, the one that has the strongest pull on its surroundings, or perhaps the one that simply looks the biggest from far away, stretched out under the light of its star? All of those are reasonable interpretations, and in astronomy, they don't always point to the same world. To see why, it helps to think about how planets are built. A planet isn't a solid block like a stone or a mountain. Even the rocky ones have layers, atmospheres, and internal structures. The giant planets take this complexity and multiply it many times over. They're not just big balls sitting in space. They're dynamic systems with deep interiors, thick atmospheres, strong magnetic fields, and ongoing interactions with their stars. Because of that, there are several different ways to describe how big a planet is, and each one tells a slightly different story. One of the most common measures is radius or diameter. This is the simple idea of how wide a planet is from one side to the other. When a planet passes in front of its star and blocks some of the light, astronomers can estimate how much of the star's surface is being covered. From that, they can work out the planet's size. This method has been incredibly powerful, and it's one of the main reasons we know about so many exoplanets today. But it also comes with a subtle bias. It favours planets that are large and close to their stars, because those planets create bigger, more noticeable dips in starlight. That means some of the largest planets on our lists are also the ones that happen to be easiest to see with this technique. Another important measure is mass. This tells us how much material a planet contains, how heavy it is, even if it doesn't look particularly wide. Mass is often measured by observing how much a planet tugs on its star. As a planet orbits, its gravity pulls the star slightly back and forth. This creates a small wobble in the star's motion, which can be detected by carefully studying the star's light. A planet with a lot of mass will create a bigger wobble. A lighter planet will create a smaller one. Now here's where things start to get interesting. A planet can be very massive without being very large in diameter. As planets grow more massive, their gravity compresses their material more tightly. At a certain point, adding more mass doesn't make the planet much bigger, it actually makes it denser. Jupiter is a good example of this. If you were to add more and more material to Jupiter, making it heavier and heavier, its diameter wouldn't increase very much. In fact, it might even start to shrink slightly. The extra gravity would squeeze the planet into a more compact shape. So when someone says the largest planet, they might be talking about the widest one, or they might be talking about the heaviest one, and those two titles don't always go to the same object. Then there's density, which is a combination of size and mass. Density tells us how much stuff is packed into a given volume. A planet with low density might be very large but relatively light, like a giant cloud held together by gravity. A planet with high density might be smaller but extremely heavy, packed with material under intense pressure. Some of the largest looking planets discovered so far have incredibly low densities. If you could find a bathtub big enough, and if the laws of physics were feeling especially cooperative that day, they might even float in water. That's how puffed up they are. Of course, you can't actually put a planet in a bathtub, but the comparison gives you a sense of how unusual these worlds can be. Another way to think about largest is in terms of influence. A very massive planet can dominate its surroundings, shaping the orbits of other planets, capturing moons, and controlling the flow of dust and debris in its system. In that sense, size isn't just about physical dimensions, it's about presence. How much of a mark does this planet leave on the space around it? Jupiter, again, is a good example close to home. It has dozens of moons, a powerful magnetic field, and a gravitational reach that extends far beyond its visible atmosphere. It plays a role in shaping the entire architecture of the solar system. Now imagine a planet even more massive than Jupiter. Its sphere of influence would be even larger. It might control the movements of other planets in its system in ways that are hard to predict. It could shape the disk of material around a young star, affecting what kinds of worlds form nearby. So in that sense, the largest planet might be the one that leaves the biggest gravitational footprint, not just the one that looks the widest through a telescope. There's also the question of where a planet ends. For rocky planets like Earth, the boundary is fairly clear. You have solid ground, then atmosphere, then space. For gas giants, the boundary is much fuzzier. Their atmospheres gradually thin out as you move away from the centre, fading into space rather than ending at a sharp edge. So when astronomers say a gas giant has a certain radius, they're usually choosing a specific level in the atmosphere where the pressure or opacity reaches a defined value. It's a practical choice, not a natural wall. In a sense, the planet doesn't have a single obvious surface. It's more like a deepening mist of gas that becomes thicker and denser as you move inward. That means two scientists could, in theory, use slightly different definitions and come up with slightly different sizes for the same planet. In practice, the field is settled on standard conventions, but the underlying reality remains a bit soft around the edges. Another layer of complexity comes from the fact that planets are not perfect spheres. Many of them spin, and when they spin, they tend to bulge at the equator and flatten slightly at the poles. Jupiter and Saturn both show this effect clearly. They're wider around the middle than they are from top to bottom, so when we talk about their diameter, we usually mean an average value. But even that average hides a bit of shape and motion inside it. Then there's time. A planet's size is not necessarily fixed over its entire lifetime. Young giant planets can be much larger than older ones. When a planet first forms, it can be hot and swollen, still holding on to the energy from its birth. Over time, as it radiates that heat away into space, it can cool and contract. For planets that orbit close to their stars, this natural cooling can be counteracted by constant heating from the star. That's one of the reasons some of the largest planets discovered are so close to their suns. The heat keeps their atmospheres expanded, making them look bigger than they might otherwise be. So when we measure a planet's size, we're capturing it at a particular moment in a long, slow process of change. The largest planet ever discovered might not stay that way forever, even if nothing new is found. It might gradually shrink as its atmosphere evolves. All of this means that largest is not a single, simple property. It's a bundle of related ideas, each one highlighting a different aspect of what a planet is and how it behaves. There's also a subtle distinction between what we can measure and what we can infer. For many exoplanets, we only know their size, not their mass. For others, we know their mass but not their size. Only a smaller group has both measurements, which allows scientists to calculate density and get a clearer picture of what the planet is made of. So when a list of the largest planets is published, it often depends on which planets have enough data available to be compared fairly. There may be even larger worlds out there that we simply haven't measured well enough yet to include. That brings in another layer of meaning to the word largest. It doesn't just refer to what exists, it refers to what we know exists. Our view of the universe is shaped by our tools, telescopes, instruments, observation time, and the methods we use to interpret data all play a role in what shows up in our catalogues. As those tools improve, the list of known planets changes, new giants appear, old records are broken, so the largest planet ever discovered is always a temporary title. It's a snapshot of our knowledge at a particular moment in history. There's something quietly fitting about that. The universe doesn't seem to like final answers. It offers us better and better approximations instead. Another interesting angle is how we decide what counts as a planet in the first place. We touched on this earlier, but it becomes especially important here. There is a fuzzy boundary between very large planets and very small stars, especially brown dwarfs. Brown dwarfs can be several times more massive than Jupiter. They don't shine like true stars, but they can glow faintly from internal heat and brief periods of limited fusion. Some of them even have disks of material around them, and possibly their own planets. So if we're not careful, the largest planet on a list might actually be something that belongs in a different category altogether. Astronomers often use a mass limit to draw the line. Objects above a certain mass, usually around 13 times the mass of Jupiter, are considered likely to be brown dwarfs rather than planets, because that's roughly the point where deuterium fusion can occur in their cores. But even that boundary is debated. Some scientists argue that how an object forms is more important than how massive it is. If it formed in a disk around a star like a planet, then it should be called a planet even if it's very massive. If it formed by collapsing from a cloud of gas like a star, then it should be called a brown dwarf, even if it's relatively light. This means that two objects with similar sizes and masses could be classified differently depending on their history, which we often can't observe directly. So when we talk about the largest planet, we're also stepping into a discussion about definitions, categories, and how humans draw lines in a universe that doesn't always respect them. There's a gentle irony here. We use precise numbers, careful measurements, and formal definitions to describe these distant worlds. But the reality itself is often messy, overlapping, and hard to pin down. The more closely we look, the more we find exceptions, edge cases, and objects that sit comfortably in the grey areas. In a way, that makes the question of largest more interesting, not less. It turns it from a simple ranking into an exploration of how planets work, how stars and disks give rise to different kinds of worlds, and how our own understanding evolves over time. There's also a human side to this. We like superlatives. The biggest, the fastest, the farthest. They give us a way to frame the vastness of the universe in terms that feel approachable. Saying this planet is twice the size of Jupiter is easier to picture than reciting long strings of kilometers and scientific notation. But even those comparisons are stepping stones rather than final destinations. They're ways of connecting something unimaginably distant to something we already know. As you sit with this idea, you might notice how the word largest begins to feel less like a destination and more like a doorway. It opens into questions about formation, physics, classification, and observation. It invites you to think about not just how big a planet is, but how it came to be that way, how it interacts with its surroundings, and how we came to know about it at all. How do astronomers actually discover these distant giants? How do they turn tiny changes in light and motion into pictures of worlds hundreds or thousands of light years away? If you were able to drift backward in time, not just years or centuries, but billions of years, long before Earth had oceans, before the sun had settled into its steady glow, before even the idea of planets existed, you would find yourself in a very different kind of scene. Not a sky full of stars and worlds, but something quieter and more diffuse. A wide, slow-moving cloud of gas and dust spread across space like a faint drifting mist. This is where the story of planets begins, not with solid ground or swirling storms, but with particles so small they barely seem like they could ever become anything at all. These clouds, often called stellar nurseries, are made mostly of hydrogen and helium, with a sprinkling of heavier elements, things like carbon, oxygen, silicon and iron. These heavier ingredients are the leftovers of earlier generations of stars that lived, burned, and eventually scattered their material back into space through winds or explosions. So even at the very start of planet formation, there's already a sense of history woven into the scene. The atoms that will one day become part of a planet, or a mountain, or even a living thing, have already been through at least one cosmic lifetime. At some point, something disturbs this quiet cloud. It might be a shock wave from a nearby supernova, the gravitational pull of a passing star, or simply the slow, uneven motion of the cloud itself. Whatever the cause, a region of the cloud begins to collapse under its own gravity. As it does, it spins, very gently at first, then faster as it pulls inward. The material flattens into a wide, rotating disk, with most of the mass collecting at the centre. This central region grows hotter and denser, eventually becoming a star. Around it, the disk remains, a broad, thin plain of gas and dust circling the newborn sun. This disk is where planets take shape. If you imagine looking at this disk from above, it might remind you of a vinyl record or a pancake of mist and grit, slowly turning in the dark. But unlike a record, it isn't smooth. It's full of tiny particles, grains of dust, ice crystals, and clumps of gas, all moving, colliding, and drifting past one another. At first, these particles are incredibly small, far smaller than a grain of sand. But over time, they begin to stick together. This sticking isn't always gentle. Sometimes it's more like a soft tap that causes two grains to cling. Sometimes it's a more energetic bump that shatters them apart. But on balance, more things stick than break, and slowly, almost patiently, the grains grow into pebbles. Pebbles become rocks, rocks become boulders, and boulders, given enough time and the right conditions, become something larger still. This stage of planet formation is often called accretion, which is a simple way of saying that small things come together to make bigger things. It's not a neat, orderly process. It's messy, full of collisions, near misses, and constant motion. Imagine a crowded ice rink where everyone is drifting in different directions, occasionally bumping into one another, and sometimes forming small clusters that skate together for a while. As these clusters grow, their gravity becomes stronger. That gravity begins to pull in more material from the surrounding disk. The bigger an object gets, the more efficiently it can grow. It's a kind of cosmic snowball effect. In the inner regions of the disk, close to the star, things are warm. Ice can't survive there. Only materials like rock and metal can stay solid. This leads to the formation of rocky planets, like Earth and Mars, with solid surfaces and relatively thin atmospheres. Farther out, beyond a boundary often called the frost line, it's cool enough for water, methane, and other substances to freeze into ice. This makes a huge difference. Ice is abundant and sticky. It allows growing planetary cores to gather mass much more quickly. These cores can become large enough, fast enough, to start pulling in the light gases around them, especially hydrogen and helium. This is where the story of giant planets really begins. Once a core reaches a certain size, often thought to be around 10 times the mass of Earth, its gravity becomes strong enough to hold onto a thick atmosphere. Gas from the disk begins to fall in, not all at once, but steadily, layer by layer. Over time, this atmosphere can grow into something enormous, dwarfing the solid core hidden deep inside. This process, called core accretion, is one of the main ways scientists think gas giants form. It explains why these planets tend to have heavier elements in their centres and thick, lighter atmospheres around them. But this isn't the only path to a giant world. In some disks, especially very massive and cold ones, parts of the disk itself can become unstable. Instead of slowly building a core and then gathering gas, a large region of the disk can collapse directly under its own gravity, forming a giant planet in a relatively short amount of time. This is known as disk instability. Planets formed this way might not have a well-defined solid core at all. They may be more evenly mixed throughout, like a ball of gas and ice that never quite separated into distinct layers. Which of these processes dominates in the universe is still an open question. It may be that both happen, depending on the conditions in the disk and the environment around the young star. What makes this especially interesting for the question of very large planets is that disk instability might be more likely to produce truly massive worlds. If a large chunk of a disk collapses all at once, it can create a planet that starts its life already enormous, pushing close to the boundary between planet and brown dwarf. So when astronomers find a giant planet that seems unusually large or massive, they often wonder which path it took to get there. Did it grow slowly, patiently pulling in gas over millions of years, or did it form in a sudden dramatic collapse of a swirling cloud? The answers are written in things like the planet's composition, its orbit, and how it interacts with its star. As these young planets form, they don't stay neatly in place. The disk around a star isn't a calm, empty stage. It's a dynamic environment, full of gas flows, pressure waves, and interactions between growing worlds. These forces can cause planets to migrate, slowly moving inward or outward from where they originally formed. This migration is one of the reasons we find giant planets very close to their stars, even though we think they usually form farther out. A planet might begin its life in the colder outer regions of the disk, gather a thick atmosphere there, and then gradually spiral inward, ending up in a tight, fast orbit near its sun. During this journey, it can pass through regions where other planets are forming. It can disrupt their growth, scatter them into new orbits, or even fling them out of the system entirely. In that way, the birth of a giant planet can shape the entire architecture of a planetary system. So when we look at a very large planet in another star system, we're often seeing the result of a long, complex history, a story that involves not just the planet itself, but everything else that was forming around it at the same time. There's also a sense of timing involved. The disk of gas and dust around a young star doesn't last forever. Over a few million years, it gets blown away by the star's radiation or pulled into planets and other objects. If a growing planetary core doesn't reach that critical size in time, it may never become a gas giant at all. It might end up as a large rocky or icy world instead, with only a thin atmosphere. So the difference between a modest planet and a massive oversized one can come down to a kind of cosmic race. Can the core grow fast enough before the gas disappears? This helps explain why giant planets are more common around certain types of stars. Stars that are richer in heavy elements tend to have disks with more solid material. That makes it easier for cores to form and grow quickly, increasing the chances of creating large planets. In other words, even at the scale of entire solar systems, chemistry matters. As these planets continue to evolve, they don't just sit quietly in their orbits. They interact with their stars in subtle and not so subtle ways. A giant planet close to its star can be tidally locked, always showing the same face to the star, much like the moon does to Earth. This creates extreme temperature differences between its day side and night side, driving powerful winds through its atmosphere. Over time, these winds can redistribute heat, shape cloud patterns, and even affect how the planet's size changes. A constantly heated atmosphere can remain expanded, keeping the planet looking larger than it might otherwise be. Meanwhile, inside the planet, slow processes are at work. Heat from formation leaks out. Materials may separate, with heavier elements sinking toward the center and lighter ones rising. Magnetic fields can be generated by the motion of conductive materials deep within. All of these processes contribute to what the planet looks like and how it behaves billions of years after it was born. What's striking is how much of this story happens out of sight. We can't watch a planet form directly, at least not in detail. The The disks are too far away, the timescale's too long. Instead, astronomers piece together this narrative by looking at many different systems at different stages of development. Some stars are very young, still surrounded by thick disks. Others are middle-aged, with a few planets already in place. Some are old, with systems that have settled into long-term stability. By comparing these snapshots, scientists build a kind of time-lapse of planetary birth and growth. This approach has revealed something important for the search for the largest planets. There doesn't seem to be a single, universal recipe. The universe is flexible. It can make small, rocky worlds and these enormous gas-dominated giants, sometimes in the same system, sometimes in very different ones. And the largest planets, the ones that stretch our definitions, often come from environments that were especially rich, especially massive, or especially dynamic. Big disks around big stars, regions where gravity and motion had a lot of material to work with. So when you hear about a planet that's nearly twice the size of Jupiter, or one that seems to sit right at the edge of being a star, you're hearing the end result of a long chain of events that began in a quiet, drifting cloud of dust and gas. There's something gently grounding about that. Even the most extreme worlds we can imagine start from the same basic ingredients. Tiny particles, simple forces, time. As you let this process settle in your mind, you might picture it not as a single moment, but as a slow, steady flow. A disk turning, particles meeting, gravity tugging, heat building and fading, orbit shifting, all of it unfolding over spans of time so long that human history would fit into a thin line at the very end. And yet, through careful observation and patient study, we found ways to read the traces of that process in the light of distant stars. If you line up all the planets we know about, both the ones close to home and the ones circling distant stars, a pattern starts to appear. It's not just a smooth scale from small to large, like pebbles becoming rocks and then boulders. Instead, planets tend to fall into families, groups defined not only by size, but by what they're made of and how they behave. And when we start talking about the biggest worlds ever found, those families become especially important, because each one comes with its own natural limits. Let's begin with the idea of a gas giant, since this is the category most people picture when they imagine a truly enormous planet. In our own solar system, Jupiter and Saturn are the classic examples. They're mostly made of hydrogen and helium, the two lightest and most abundant elements in the universe. These planets don't have solid surfaces in the way Earth does. Instead, their atmospheres gradually become denser and denser as you move downward, until the gases behave more like liquids and, deeper still, like compressed exotic forms of matter under immense pressure. Because hydrogen and helium are so light, gas giants can grow very large in diameter without needing to be incredibly heavy, at least at first. Their outer layers can stretch far out into space, creating a wide, puffy appearance. This is one of the reasons many of the largest-looking exoplanets discovered so far are gas giants. But even gas giants face a kind of ceiling. As a gas giant grows more massive, its gravity becomes stronger, and that gravity starts to squeeze the planet inward. At small to moderate sizes, adding more gas makes the planet bigger. But beyond a certain point, adding more gas mostly makes it denser instead. You can think of it like stacking soft pillows. At first, adding more pillows makes the stack taller, but if you keep piling them on, the weight starts to compress the ones underneath. Eventually, the stack doesn't get much taller at all. It just gets more tightly packed. In planetary terms, this means that there's a size range where gas giants can keep expanding, but once they reach a certain mass, their radius stops increasing significantly. In fact, very massive gas giants can be about the same size as Jupiter, or even slightly smaller, despite having several times Jupiter's mass. This is one of the reasons Jupiter holds a special place in planetary science. It sits near the peak of the size curve. There are planets heavier than Jupiter, but there are very few that are significantly wider. So when astronomers find a planet that looks much larger than Jupiter, they often suspect something unusual is going on. It may not be more massive, it may simply be hotter, more inflated, or both. Heat plays a powerful role in shaping a gas giant's size. When a planet is close to its star, the intense radiation can warm its atmosphere, causing the gases to expand. This creates what are sometimes called inflated or puffed up planets. They look enormous, but their material is spread out, making them low in density. These are the kinds of worlds that often show up on lists of the largest planets by radius. They can be nearly twice as wide as Jupiter, even if they're only a fraction of Jupiter's mass. Now let's shift to the other main family of giant planets, the ice giants. In our solar system, Uranus and Neptune represent this group. They're still large compared to Earth, but they're smaller and denser than Jupiter and Saturn. Their composition includes more heavy elements, such as water, ammonia and methane, mixed with hydrogen and helium. The term ice here doesn't mean these planets are frozen solid in the everyday sense. It refers to substances that would be ices under the cold conditions of the outer solar system, even though deep inside these planets, those materials are under such high pressure and temperature that they exist in exotic fluid-like states. Because ice giants contain more heavy material relative to light gas, they tend to be smaller in diameter for a given mass. Their gravity compresses them more effectively, leading to a more compact structure. This means that ice giants are less likely to become record holders for sheer size. Even if you added more material to them, they would tend to get denser rather than much wider. In exoplanet surveys, scientists have found many worlds that fall somewhere between the classic gas giants and ice giants. These are often called sub-Neptunes or super-Neptunes, depending on their size and mass. They can have thick atmospheres, but also a substantial amount of heavier material inside. These intermediate planets add another layer of complexity to the idea of size limits. They show that there isn't a single, clean dividing line between categories. Instead, there's a gradual transition, with planets blending into one another across a range of properties. So where exactly do the limits of size come from? Part of the answer lies in the physics of matter under pressure. As a planet grows, the pressure in its interior increases. For gas giants, this leads to hydrogen behaving in unusual ways. At very high pressures, hydrogen can become metallic, meaning it conducts electricity like a metal. This metallic hydrogen is thought to be responsible for Jupiter's powerful magnetic field. But as the pressure increases, the material becomes less compressible. It resists being squeezed further. This is what creates the plateau in the size of massive planets. Beyond a certain point, gravity can't make the planet much bigger. It can only make it heavier and denser. Another part of the limit comes from formation itself. There is only so much material available in a typical protoplanetary disk. Even in very massive disks, the amount of gas and dust is finite. A planet can't grow indefinitely unless it's in an environment with an extraordinary amount of material to draw from. And then there's the boundary between planets and stars. As a giant planet becomes more massive, its core temperature rises. At around 13 times the mass of Jupiter, conditions can become hot and dense enough for deuterium fusion to occur. Deuterium is a heavier form of hydrogen, and fusing it releases energy. Objects that can fuse deuterium are often classified as brown dwarfs rather than planets. They're not true stars because they can't sustain long-term hydrogen fusion, but they're also not quite planets anymore. This creates a kind of upper mass limit for what we usually call a planet. It's not a sharp, physical wall, but a convention based on what kinds of nuclear reactions can happen inside the object. So when we talk about the largest planet, we're usually talking about something that sits below this threshold. Something that is big, but not so big that it crosses into the realm of star-like behaviour. Within that range, size in terms of diameter tends to peak around Jupiter's scale, with some variation depending on temperature and composition. That's why so many of the largest looking planets cluster around 1 to 2 times Jupiter's radius, even if their masses vary widely. Another factor that shapes size is age. Young giant planets are often larger than older ones. They start out hot and inflated, still glowing with the heat of their formation. Over time, they cool and contract. This means that if you observe a young planetary system, you might find giants that look unusually large compared to similar planets in older systems. Given enough time, those same planets might shrink and become more compact. So a list of the largest planets is also, in a way, a list of planets caught at particular moments in their lives. There's also the role of atmosphere loss. Planets that orbit close to their stars can lose parts of their atmospheres over time due to intense radiation. This can strip away the outer layers of gas, making a planet smaller and denser. Some scientists think that certain classes of planets we see today, such as hot Neptunes or super-Earths, might be the exposed cores of what were once much larger gas giants. If that's true, then the largest planets may represent a phase that some worlds pass through, rather than a permanent state. When you put all of this together, the idea of a hard, universal size limit starts to feel less rigid and more like a set of overlapping constraints. Physics, chemistry, formation history, environment and time all play roles in shaping how big a planet can become and how big it remains. There's something quietly elegant about that. The universe doesn't hand out simple categories with fixed boundaries. It offers ranges, trends and exceptions. It lets worlds exist along a spectrum rather than in neat boxes. From a practical standpoint, this also means that when astronomers announce the discovery of an exceptionally large planet, they often follow it with a series of careful clarifications. How massive is it? How hot is it? How old is the system? How close is the planet to its star? Each of these details helps place the planet within the broader context of what's physically possible. And sometimes, those details reveal that the planet isn't quite as extreme as it first appeared. A planet that looks enormous might turn out to be very light and inflated. One that seems incredibly massive might actually be on the border of being a brown dwarf. Still, even with those caveats, these giant worlds remain fascinating. They show us what happens when the basic ingredients of the universe, gas, dust, gravity, and time, are given the right conditions to build something on a truly grand scale. There's also a broader implication here for how we think about planetary systems as a whole. The presence of a very large planet can shape the destiny of everything else around it. It can influence where smaller planets end up, whether stable orbits can exist, and how material moves through the system. In some systems, a giant planet might prevent smaller worlds from forming close to the star by sweeping up or scattering the material they would need. In others, it might migrate inward and disrupt already formed planets, changing their orbits or ejecting them into space. So the limits of size are not just about the planet itself, they're about the balance of the entire system. As you let this settle, you might picture a young star surrounded by a wide, glowing disk, with clumps forming, growing, and moving through it. Some of those clumps will become modest worlds, others will grow into giants, and a few, under the right circumstances, will push right up against the boundaries of what we're comfortable calling a planet. Those boundary-pushing worlds are often the ones that catch our attention. They're the ones that make headlines, that get described as record breakers or cosmic oddities. But beneath that surface excitement is a quieter story. A story about how nature builds things, how it balances forces, and how even the largest creations are shaped by the same basic rules as the smallest ones. When people first start thinking about giant planets, there's almost always one name that comes to mind before any other: Jupiter. It sits there in the night sky, bright enough to be seen with the naked eye, steady and calm like a quiet landmark among the shifting patterns of stars. Long before telescopes, long before anyone knew what a planet really was, humans noticed Jupiter and gave it a place in their stories, their calendars, and their sense of the heavens. So when astronomers go searching for worlds that are bigger than anything we know, Jupiter naturally becomes the reference point. It's the familiar giant, the one we measure everything else against, the yardstick for large in planetary terms. Let's take a slow, careful look at what makes Jupiter what it is. because understanding this one world makes it much easier to appreciate just how unusual some of the larger planets out there really are. Jupiter is massive in a way that's hard to translate into everyday experience. It contains more than twice the mass of all the other planets in our solar system combined. If you were to scoop up Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and somehow press them together into a single object, Jupiter would still outweigh them. That alone gives it a kind of gravitational authority in our corner of the galaxy. Its diameter is about 11 times that of Earth. That means you could line up 11 Earths side by side across Jupiter's face and still have room to spare. And as impressive as that is, it's the volume that really stretches the imagination. More than 1,000 Earths could fit inside Jupiter's vast interior. Yet for all that size, Jupiter is mostly made of the lightest stuff in the universe, hydrogen and helium. If you could somehow remove all of Jupiter's material and lay it out in front of you, you wouldn't see mountains of rock or oceans of water. You'd see enormous quantities of gas compressed under gravity into layers that behave in ways we don't usually encounter on Earth. The outermost part of Jupiter is its atmosphere, a thick, swirling envelope of clouds and storms. Those familiar bands you see in telescope images, the light and dark stripes running parallel to the equator, are actually powerful jet streams. They're winds that race around the planet at hundreds of kilometers per hour, circling it in alternating directions. Then there's the Great Red Spot, a storm so large that Earth could fit inside it. It's been raging for at least a few hundred years, possibly longer. While storms on Earth come and go, shaped by continents and oceans, Jupiter's storms can persist for generations, fueled by the planet's internal heat and rapid rotation. That rotation is another key feature. Jupiter spins fast. A day on Jupiter lasts just under 10 hours. Because it's so large that rapid spin gives it a noticeable bulge at the equator, it's not a perfect sphere. It's slightly squashed at the poles and wider around the middle, like a soft ball spun just a little too quickly. Beneath the visible clouds, the atmosphere becomes thicker and denser. Hydrogen gas transitions into a liquid-like state, and deeper still, under immense pressure, it becomes metallic hydrogen. This is a strange form of matter, where hydrogen, usually a simple gas, behaves like a metal and conducts electricity. It's this metallic hydrogen layer that's thought to generate Jupiter's powerful magnetic field. That magnetic field is the strongest of any planet in the solar system. It extends millions of kilometers into space, creating a vast region around Jupiter where charged particles are trapped and guided by invisible magnetic lines. Jupiter's influence doesn't stop with its atmosphere and magnetism. It has a whole family of moons, more than 90 known so far. Some of them are small, irregular chunks of rock and ice. Others are worlds in their own right. The 4 largest, known as the Galilean moons, were discovered by Galileo Galilei in 1610. Io, Europa, Ganymede, and Callisto. Each one is different, and each one has played a role in shaping how we think about what moons and planets can be. Io is the most volcanically active body in the solar system, its surface constantly reshaped by eruptions driven by gravitational tug-of-war between Jupiter and the other moons. Europa hides a vast ocean beneath a shell of ice, an ocean that might contain more water than all of Earth's oceans combined. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and it even has its own magnetic field. Callisto is heavily cratered, a kind of record of ancient impacts frozen in time. So when we talk about Jupiter, we're not just talking about a planet, we're talking about a miniature system, a collection of worlds held together by a central giant. In the broader story of planet formation, Jupiter likely played a key role in shaping the rest of the solar system. Its gravity influenced the distribution of material in the disk that surrounded the young sun. It may have limited the growth of Mars by sweeping away or redirecting material that might otherwise have gone into building a larger planet. There's also evidence that Jupiter didn't always sit exactly where it is now. Some models suggest that it migrated inward and then outward again during the early history of the solar system. If that's true, it would have had an even more dramatic effect on the orbits and formation of the other planets. So Jupiter isn't just big, it's influential. It's a kind of architect of the system it lives in. Because of all this, Jupiter became the natural benchmark for giant planets beyond our solar system. When the first exoplanets were discovered in the 1990s, many of them were described in terms of how they compared to Jupiter. A planet might be half the mass of Jupiter or twice the size of Jupiter. The name Jupiter itself became part of the language of exoplanet science. Terms like hot Jupiter emerged to describe gas giants that are similar in mass to Jupiter but orbit very close to their stars. These worlds challenged expectations, because in our own system, giant planets are far from the Sun. Finding them hugging their stars forced scientists to rethink how planets move and settle into their final orbits. So in a way, Jupiter is not just a benchmark, it's a starting point for surprises. It represents a kind of balance point in planetary physics. It's massive enough to dominate its surroundings, but not massive enough to become something else, like a star or brown dwarf. It's large enough to hold a thick, deep atmosphere, but not so large that its gravity compresses it into a much smaller shape. As we talked about earlier, adding more mass to a gas giant beyond Jupiter's range doesn't make it much bigger in diameter, it mostly makes it denser. That's why Jupiter sits near the top of the size curve for planets. It's close to the maximum width that a typical gas giant can have without special circumstances. This is what makes the largest looking exoplanet so intriguing. When scientists find a planet that appears significantly wider than Jupiter, they know something unusual is happening. The planet might be extremely hot, it might be very young, its atmosphere might be in a highly inflated state. So Jupiter becomes a kind of reference anchor. It tells us what a normal giant planet looks like under more moderate conditions. It also gives us a nearby laboratory to test our theories. We can send spacecraft to Jupiter, we can fly past it, orbit it, and drop probes into its atmosphere. Missions like Galileo and Juno have given us direct measurements of its gravity field, its magnetic field, its atmospheric composition, and its internal structure. These detailed observations help scientists build models of how giant planets work, and those models can then be applied cautiously to the distant giants we can only study through light curves and spectra. Jupiter's atmosphere, for example, contains clues about the conditions in the early solar system. The relative amounts of different elements can tell us about where and how it formed. Did it form quickly? Did it gather material from a wide region of the disk? These are questions that connect Jupiter's story to the stories of giant planets everywhere. There's also a subtle psychological role that Jupiter plays. Because it's visible from Earth and easy to spot, it feels more real than most of the distant exoplanets we talk about. You can step outside on a clear night and see it for yourself. A bright point of light that you now know is a world larger than 1,000 Earths, surrounded by dozens of moons, wrapped in storms that have lasted longer than most human civilizations. That sense of connection makes it easier to grasp the idea that there could be worlds even larger, even more extreme, out there among the stars. When astronomers say a planet is 2 times the radius of Jupiter, they're not just giving a number, they're inviting you to take everything you know about Jupiter, its size, its storms, its gravity, its family of moons, and then imagine something that stretches even farther into space. It's worth pausing on that for a moment. Imagine Jupiter in your mind. Now imagine a version of it that's nearly twice as wide. The storms would be larger. The gravity at the cloud tops might feel gentler because the mass is spread out. The atmosphere would extend even farther, fading slowly into space. It would still be a gas giant, but it would feel like a different kind of presence, something more diffuse, more expansive. This comparison also highlights an important point. Jupiter is, in many ways, a stable giant. It's been around for billions of years, and it will likely remain much as it is for billions more. Some of the larger-looking exoplanets may not have that kind of long-term stability. Their inflated atmospheres could be temporary, slowly eroded by their stars, so Jupiter becomes a kind of baseline for what a long-lived giant planet looks like. Another reason Jupiter is so central to these discussions is its role in our search for life. While Jupiter itself is not a place where life as we know it could exist, its moons, especially Europa, have become prime targets for exploration. The idea that a moon of a gas giant could harbour a subsurface ocean and potentially the conditions for life has expanded the way scientists think about habitable environments. This means that giant planets can be important not just as objects of interest themselves, but as hosts for other worlds that might be more welcoming. So when we talk about very large planets in other systems, part of the question becomes whether they might also have families of moons, and whether those moons might have environments shaped by the gravity, radiation and heat of their giant parent. That adds another layer to the meaning of big. It's not just about the planet's own size, it's about the size of the system it creates around itself. Jupiter's magnetosphere, for example, is so large that if it were visible from Earth, it would appear larger in the sky than the Moon. It's an invisible bubble of influence that extends far into space, interacting with the solar wind and shaping the environment around the planet and its moons. So when we look at a massive exoplanet, we can wonder about the invisible structures around it, the magnetic fields, the radiation belts, the regions where charged particles dance and spiral. These are all parts of what it means to be a giant in space. In that sense, Jupiter isn't just a measuring stick, it's a model, a kind of template for what a large planet can be, what it can do, and how it can shape its surroundings. As you let this familiar giant settle in your thoughts, it becomes easier to see why astronomers often start their comparisons here. Jupiter is the known reference, the giant we can study up close, the one that anchors our imagination when we look at the data from distant stars. There comes a point when you spend enough time thinking about planets and gravity and gas and the quiet rules that seem to guide how the universe builds things, that certain expectations settle into place. You start to feel like you understand the general shape of what's possible. You learn that rocky worlds stay relatively small, that gas giants grow large but not endlessly large, that stars are the ones that truly dominate in size and mass, and somewhere in between there's a comfortable boundary where planets are supposed to stop and something else is supposed to begin. So when astronomers began to find planets that appeared larger than Jupiter by a wide margin, it felt, at first, a little like someone had quietly moved that boundary without telling anyone. Because according to many of the simple models, Jupiter is already close to the practical upper limit for how wide a planet should be. Add more material, and gravity should squeeze it down, not let it puff out. Make it heavier, and it should get denser, not broader. In that neat, tidy picture, a planet that looks much bigger than Jupiter shouldn't really exist. And yet, there they were. Not just one or two, but a growing list of worlds that seemed to stretch beyond the comfortable expectations. Planets with radii 1.5 times that of Jupiter, some approaching nearly twice its size. Worlds that, if placed in our solar system, would loom so large they would feel almost out of place, like something that wandered in from a different category entirely. At first, the natural reaction was to question the measurements. Maybe the stars were larger than expected. Maybe the dips in light were being misinterpreted. Maybe these objects weren't planets at all, but something closer to brown dwarfs or small stars. But as more data came in, from different telescopes and different methods, the picture held. These worlds were real. They were planets by most accepted definitions, and they were, in terms of sheer width, bigger than Jupiter. So the question shifted. Instead of asking whether they existed, scientists began asking how. One of the first clues came from looking at where these planets were located. Many of the largest looking planets orbit extremely close to their stars. Not at the comfortable distances we associate with Jupiter or Saturn, but in tight, fast orbits that take just a few days to complete. In these environments, the star is not a distant source of gentle warmth. It's a blazing presence in the sky, filling much of the planet's horizon, pouring energy into its atmosphere day after day, year after year. That energy does something important. It heats the planet's outer layers, and when gas heats up, it expands. This might sound simple, but on a planetary scale, the effect can be dramatic. The atmosphere of a gas giant can swell outward, becoming thicker and more extended. The planet doesn't gain much mass in this process, but it gains size, in the sense that the region where the atmosphere is dense enough to block starlight moves farther out into space. So when astronomers measure the radius of such a planet, they're often measuring the outer edge of a very expanded, very heated atmosphere. The solid core, if there is one, might not be much bigger than Jupiter's. The extra width comes from a kind of atmospheric halo, a thick envelope of gas that's been puffed up by constant heat. This idea, known as planetary inflation, has become one of the leading explanations for why some planets look so much larger than Jupiter. But even that explanation has limits. If heat alone were responsible, then all close-in gas giants should be similarly inflated. But in reality, some are, and some aren't. Two planets at similar distances from their stars with similar masses can have very different sizes. This suggests that other factors are at play. One possibility is internal heat. Some planets may have ongoing sources of energy inside them, such as slow contraction, tidal heating from gravitational interactions with their star or other planets, or even residual heat from their formation. This internal energy can add to the heating from the star, keeping the atmosphere expanded for longer periods of time. Tidal heating in particular can be significant. If a planet's orbit is slightly stretched into an oval shape rather than a perfect circle, the gravitational pull from the star changes as the planet moves closer and farther away. This changing pull can flex the planet, generating heat inside, much like bending a piece of metal back and forth can make it warm. Another factor is composition. The exact mix of elements in a planet's atmosphere and interior can affect how easily it absorbs and retains heat. Some gases are better at trapping energy than others. A planet with an atmosphere rich in certain compounds might stay puffed up longer than a planet with a different mix, even if they're otherwise similar. Then there's age. Younger planets tend to be larger. They're still hot from their formation, and haven't yet had time to cool and contract. If you observe a young system, you might catch a giant planet in a naturally inflated state, before it settles down into a more compact form. So when a planet looks too big, it might not be breaking the rules. It might simply be caught at a moment when all the conditions line up to make it appear larger than it will be in the long run. Still, some of these worlds push the idea of inflation to its limits. Even with heat, internal energy, and favourable composition, their sizes can be hard to explain fully. This has led scientists to explore more complex models, ideas involving atmospheric circulation, where strong winds transport heat deep into the planet's interior, or interactions between the planet's magnetic field and the stellar wind, which could deposit energy into the upper atmosphere, or even layered structures in the planet's interior that affect how heat moves outward. What emerges from all of this is a picture that's much less simple than the old idea of a gas giant as a static ball of gas. These planets are dynamic systems, constantly exchanging energy with their stars and their surroundings, constantly adjusting their internal balance. Another layer of strangeness comes from the boundary between planets and brown dwarfs. Some of the largest planets by size are not especially massive. They're puffy and light. But there are also objects that are extremely massive, well above Jupiter's mass, yet not much bigger in diameter. So you can end up with a situation where a planet that weighs only a fraction as much as another object looks significantly larger. This flips our everyday intuition on its head. We tend to associate size with weight. In the universe of giant planets, that connection can be surprisingly loose. And then there's the question of how these worlds form in the first place. If a planet ends up very close to its star, where it's being intensely heated, did it form there? Or did it form farther out, where conditions were cooler and more typical for giant planet formation, and then migrate inward? Most models suggest the latter. These planets likely began their lives in the colder outer regions of their systems, grew large by gathering gas there, and then slowly spiraled inward through interactions with the disk or other planets. That journey itself can be disruptive. It can strip away some of the planet's atmosphere, or it can alter its internal structure. The fact that some planets survive this process and end up as swollen giants close to their stars adds another layer of complexity to their story. So when we say, bigger than Jupiter shouldn't exist, what we often mean is that, according to the simplest, most straightforward models, planets shouldn't look like this. But the universe, as it tends to do, seems to enjoy working in the spaces between our models. There's also an observational side to this. Our methods for finding planets are more sensitive to certain kinds of worlds. Large planets close to their stars are easier to detect, both because they block more light and because they cause their stars to wobble more noticeably. This means our sample of known planets is not a perfect reflection of what's actually out there. It's a reflection of what's easiest for us to see. So it's possible that these oversized planets are not as rare as they seem, or that we're seeing a particular subset of them, the ones that are most inflated and most visible. At the same time, there may be other kinds of large planets, perhaps massive but not inflated, that are harder to detect and therefore less represented in our catalogues. This makes the idea of shouldn't exist feel a little softer. It's not just about what physics allows, it's also about what our instruments can find. There's a quiet parallel here to the way scientific understanding often unfolds. We build simple models to explain what we see. Those models work well within a certain range. Then we discover something that sits outside that range, and the models have to grow. The oversized planets serve that role in planetary science. They sit at the edges of what we think we understand, reminding us that our explanations are always provisional, always open to revision. There's also something deeply human about the way we react to these worlds. We like the idea that there are limits, that the universe follows neat, predictable patterns. Finding a planet that seems to defy those patterns can feel unsettling, but it can also feel exciting. It suggests that there's more to learn, more to uncover, more room for surprise. On a quieter level, these planets invite a kind of imaginative exercise. Picture one of these inflated giants in your mind, its star hanging enormous in the sky, filling much of the horizon, its atmosphere glowing faintly with heat, perhaps tinted by exotic chemicals. Winds racing around the planet carrying energy from the day side to the night side, gas slowly leaking away into space, forming a long invisible tail. It's a world that feels less like a solid place and more like a shifting, breathing structure held together by gravity and heat. In that sense, these planets blur not just the line between planet and star, but also the line between object and process. They're not just things, they're ongoing interactions between matter, energy and time. And that brings us back to the idea of limits. When we look for the largest planet, we're really looking for the point where one set of behaviours gives way to another, where a gas giant starts to behave more like a star, where a planet's atmosphere becomes so extended that it's no longer clear where the planet ends and space begins. These are not sharp boundaries, they're gradual transitions, which means that bigger than Jupiter isn't a single category. It's a range of possibilities, each one shaped by a different balance of mass, heat, composition, and environment. As astronomers continue to search, they may find planets that push these boundaries even further. Worlds that are larger, puffier, more massive or more extreme in their conditions, and each one will prompt a new round of questions, adjustments and refinements in our understanding. There's a quiet rhythm to this process. Observation leads to explanation. Explanation leads to expectation. Expectation leads to surprise. Surprise leads back to observation. And in the middle of that rhythm are these oversized giants, calmly orbiting their stars, unaware that they've become symbols of how much we still don't know. There's a particular kind of quiet that comes with staring at a star through a telescope. Not the quiet of silence exactly, but the quiet of patience. the kind where nothing seems to be happening, and yet everything depends on noticing the smallest possible change. A slight dimming, a tiny shift, a pattern that repeats just enough times to suggest that something, somewhere, is moving in front of something else. This is how the story of the largest planets beyond our solar system began. Not with dramatic images or sweeping views of distant worlds, but with careful watching and a willingness to trust that even the faintest signals can carry enormous meaning. Before the mid-1990s, the idea of finding planets around other stars was still more dream than reality. Astronomers suspected they were out there, of course. It seemed unlikely that our Sun would be the only star with a family of worlds. But suspicion isn't the same as evidence. For a long time, there simply wasn't a reliable way to detect planets that were so small and so faint compared to the stars they orbited. Stars are bright, planets are not. From across the vast distances of space, a planet is usually lost in the glare of its star, like a firefly next to a floodlight. So instead of trying to see the planet directly, astronomers looked for its effects. One of the first successful techniques focused on motion. A planet and a star don't actually orbit in a simple one-way relationship, with the planet circling a fixed star. In reality, both objects orbit a common centre of mass. The star moves in a small, slow wobble in response to the planet's gravity. By studying the light from a star very carefully, scientists can detect tiny shifts in its spectrum caused by this wobble. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward the red. This is called the Doppler effect, and it's the same principle that makes the sound of a passing siren change pitch as it goes by. In 1995, astronomers using this method announced the discovery of a planet orbiting a Sun-like star called 51 Pegasi. The planet, known as 51 Pegasi b, was roughly the mass of Jupiter. That alone was remarkable. But what really caught everyone's attention was its orbit. It was incredibly close to its star, completing a full orbit in just a few days. This was not what anyone expected. According to the prevailing models, giant planets like Jupiter should form far from their stars in the colder outer regions of their systems. Finding a Jupiter-mass planet hugging its star felt like discovering a polar bear living comfortably in the middle of a desert. This was the first hint that the universe might be much more flexible in how it arranges its worlds than we had imagined. As more astronomers began to use the same technique, more giant planets turned up. Many of them were similar to 51 Pegasi b, massive, close to their stars, and moving fast. These were the first of what would come to be known as hot Jupiters. At this early stage, the focus was on mass rather than size. The wobble method tells you how heavy a planet is, but not how wide it is. So these discoveries were about finding Jupiter-like masses, not necessarily Jupiter-like dimensions. But a shift came when another technique began to take centre stage. This method relied not on motion, but on light. When a planet passes directly in front of its star from our point of view, it blocks a small fraction of the star's light. The star gets very slightly dimmer for a short period of time. If this dip in brightness happens at regular intervals, it suggests that a planet is orbiting and crossing the star's face on a predictable schedule. This is known as the transit method, and it opened a new window onto the study of exoplanets. By measuring how much light is blocked, astronomers can estimate the planet's size. A bigger planet blocks more light, a smaller one blocks less. When the first transiting giant planets were discovered, scientists could for the first time compare mass and size for the same world. And that's when the surprises really began. Some of these planets were not just massive, they were huge. Their radii were significantly larger than Jupiter's, sometimes by a wide margin. They were puffed up, swollen, and in some cases astonishingly low in density. It was as if the familiar giant planet template had been stretched and softened, like a balloon filled a little too much. One of the early standouts was a planet called HD 2-945b, often nicknamed Osiris. It was one of the first planets observed both by its gravitational effect on its star and by its transit across the star's face. The measurements showed that it was larger than Jupiter, but not much more massive. This meant it was far less dense. Its atmosphere was extended and loosely held, and observations even suggested that it was losing some of that atmosphere into space, forming a kind of trailing cloud of gas behind it. This was a new kind of world. A giant planet, yes, but one that was being actively shaped by its star in a way Jupiter never experiences. As transit surveys expanded, more of these inflated giants were found. Some of them were nearly twice the size of Jupiter. They earned informal labels like superpuffs or bloated planets, terms that captured the sense that these worlds were not just big, but exaggerated. Then came space-based observatories designed specifically to hunt for transits. One of the most influential was the Kepler Space Telescope. Launched in 2009, Kepler stared at a single patch of sky, monitoring the brightness of more than 100,000 stars at once. Its goal was to catch the tiny dips caused by planets passing in front of their stars. Over its mission, Kepler discovered thousands of exoplanets and candidates, ranging from small rocky worlds to large gas giants. It showed that planets are common, that they come in a wide variety of sizes, and that systems very different from our own are the norm rather than the exception. Among Kepler's discoveries were many large planets, including some that pushed the upper limits of size. What made these discoveries especially valuable was the sheer volume of data. Instead of just a handful of unusual worlds, scientists now had a population to study. They could look for patterns, they could compare sizes, masses, temperatures and orbits across hundreds of planets. This allowed them to begin teasing out why some planets become super Jupiters in size, while others remain more compact. Another mission, the Transiting Exoplanet Survey Satellite, or TESS, built on Kepler's legacy. Instead of focusing on a single region of the sky, TESS scans nearly the entire sky, looking for transiting planets around relatively nearby, bright stars. This has made it easier to follow up on discoveries with ground-based telescopes and study these planets in more detail, including their atmospheres. Through these combined efforts, the catalogue of known giant exoplanets has grown into the thousands, and within that catalogue, a subset stands out as especially large, especially inflated or especially extreme. Some of the planets that have drawn attention over the years include worlds like WASP 17b, with a radius nearly twice that of Jupiter, and HAT P67b, one of the least dense planets known. These are not just slightly bigger versions of Jupiter. They are worlds that occupy a different part of the parameter space, where gravity, heat, and composition combine in unusual ways. The discovery of these planets often follows a similar pattern. First, a survey telescope notices a small, regular dip in a star's brightness. That suggests a planet might be passing in front of it. Then, astronomers use other telescopes to confirm the signal and rule out other possibilities, like a second star or a background object. Once the planet is confirmed, they measure how much the star wobbles to estimate the planet's mass. With size and mass in hand, they can calculate density, which gives clues about what the planet is made of and how its interior might be structured. For some of these supersized planets, the density is so low that it raises eyebrows. It suggests that the atmosphere is extremely extended, possibly stretching thousands of kilometers above the deeper layers of the planet. In a few cases, astronomers have been able to study the atmospheres of these giants directly by analysing the starlight that passes through the planet's atmosphere during a transit. Different gases absorb different wavelengths of light, leaving telltale signatures in the star's spectrum. Through this technique, scientists have detected elements like sodium, water vapour, carbon monoxide, and even hints of more exotic compounds in the atmospheres of some giant exoplanets. This adds another dimension to the idea of discovery. It's not just about finding a big planet, it's about beginning to understand what it's like. There's also a sense of scale involved in how these discoveries are made. A planet that's twice the size of Jupiter might be hundreds or thousands of light years away. The light we use to detect it left its star long before humans built cities or wrote history. So in a very real sense, the discovery is a kind of time travel. We're seeing these worlds as they were in the distant past, not as they are now in any absolute sense. That adds a quiet layer of wonder to the process. The planets we call the largest ever discovered might not even exist in the same form anymore. They might have lost atmosphere, changed orbits, or been affected by their stars in ways we can't yet see. But in the light reaching our telescopes, they are frozen in a moment of their long lives, large and swollen and quietly circling. Another interesting aspect of these discoveries is how often they come from collaborative efforts. It's rarely a single astronomer or a single telescope that finds and confirms a super Jupiter. It's teams spread across the world, using different instruments, sharing data, and building a picture piece by piece. There's something fitting about that. Worlds that are too large to imagine easily are found through networks of people working together, each one contributing a small part to the larger story. And as the catalogue grows, so does the sense that these oversized planets are not just rare oddities. They're part of a broader population of giant worlds that occupy a wide range of conditions. Some orbit hot, bright stars, others circle cooler, dimmer ones. Some have circular orbits. Others follow long, stretched paths that carry them close to their stars and then far away again. Each variation adds another data point to the effort to understand what makes a planet grow large, what keeps it inflated, and what eventually brings it back down toward a more compact state. There's also a gentle shift in perspective that comes with this growing knowledge. Early on, Jupiter felt like a giant among giants, the king of planets, unmatched in size and presence. Now, Jupiter feels more like a familiar example in a much broader family. Still impressive, still important, but no longer alone at the top of the scale. The discovery of super Jupiters has expanded the range of what we consider normal. It's shown that the universe can produce worlds that make even our largest planet look moderate by comparison. And yet, despite all the data and measurements, these discoveries still carry a sense of mystery. We can calculate radii and masses, we can model atmospheres and interiors, but we can't visit these worlds. We can't watch their storms directly or feel their gravity. So they remain, in a way, quiet presences in the background of our knowledge. Known, but not truly familiar. You might picture a star field dotted with invisible paths, each one marking the orbit of a planet we've discovered. Some paths are small and close to the star, others stretch farther out, and among them are these wide, swollen orbits traced by planets that seem almost too large to be real. Each one was found not by a dramatic image, but by a careful noticing of something subtle. A star dimming just a little, a spectrum shifting just a bit. From those small signs, entire worlds have emerged in our understanding. There's a gentle paradox at the heart of measuring distant planets. The farther away a world is, the more carefully you have to look, and the more carefully you look, the more you begin to rely on things you can't see directly. Astronomers don't point a telescope at a faraway star and watch a tiny globe drifting across space like a marble on a table. Instead, they study light, patterns, timing, small changes that repeat often enough to suggest that something solid and persistent is quietly making its way around a distant sun. So when we talk about measuring the size of a planet that might be hundreds or thousands of light years away, what we're really talking about is a careful interpretation of how that planet affects the light and motion of its star. Let's begin with the most familiar tool in this part of the story, the transit method. Imagine a star as a bright, steady lamp in the distance. Now imagine a small object passing in front of it. For a moment, the light reaching you dims slightly. The lamp hasn't changed. The object is just blocking a small part of its glow. On Earth, this kind of change would be obvious. You'd see a shadow. In space, across immense distances, it's far more subtle. The dimming might be less than 1% of the star's total brightness, Sometimes it's just a few hundredths of a percent. But with sensitive instruments and careful observation, that tiny dip can be measured. When a planet passes in front of its star from our point of view, it creates a light curve. This is a graph that shows how the star's brightness changes over time. The shape of that curve carries a lot of information. The depth of the dip tells astronomers how much of the star's light is being blocked. A deeper dip means a larger planet. A shallower dip means a smaller one. To turn that dip into a physical size, scientists also need to know the size of the star. If you know how wide the star is, and you know what fraction of its light is being blocked, you can calculate the planet's radius using simple geometry. For example, if a planet blocks 1% of the star's light, then its diameter is about 1/10 of the star's diameter. It's not exact, but it's close enough to give a solid estimate. So a big part of measuring a planet's size actually comes down to measuring the star. Astronomers study the star's spectrum, its brightness, and its temperature to estimate its radius and mass. The better they understand the star, the more accurately they can understand the planet. The timing of the transit also matters. The length of time the planet takes to cross the star gives clues about its orbit. Combined with the period between transits, this can tell scientists how far the planet is from the star and how fast it's moving. This information doesn't directly affect the planet's size, but it helps build a complete picture of the system, which can be important for understanding things like atmospheric expansion and temperature, which in turn relate back to why the planet might look larger than expected. But the transit method isn't the only way to estimate size, and it doesn't work for every system. For a transit to be visible from Earth, the planet's orbit has to be lined up just right. It has to pass directly between us and its star. Most planetary systems aren't oriented this way, which means many planets never transit from our perspective. So astronomers use other methods as well, especially when they want to combine size with mass to understand a planet's density. One of the most important of these is the radial velocity method, which we touched on earlier. This technique measures how much a star wobbles due to the gravitational pull of an orbiting planet. By analysing shifts in the star's spectrum, scientists can estimate the planet's mass. When you have both the size from transits and the mass from radial velocity measurements, you can calculate density. And density is a powerful clue. It tells you whether a planet is likely rocky, icy, or mostly gas. For the largest planets, this is especially revealing. A giant planet with a low density is likely to be highly inflated, with a thick, extended atmosphere. A giant planet with a high density might be more compact, possibly approaching the boundary between planet and brown dwarf. Sometimes, astronomers can even refine size measurements by looking at the planet's atmosphere during a transit. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. Different gases absorb different wavelengths of light, leaving small fingerprints in the star's spectrum. By studying these absorption features, scientists can learn about the composition and thickness of the atmosphere. This can help them understand where the edge of the planet is, at least in terms of where the atmosphere becomes opaque enough to block light. This matters because, as we discussed before, gas giants don't have a solid surface with a clear boundary. Their atmospheres gradually thin out, so the size we measure depends on where we choose to draw the line. In practice, astronomers usually define a planet's radius as the level in the atmosphere where the optical depth reaches a certain value, meaning where the atmosphere becomes thick enough to block a significant amount of light. It's a practical choice that allows for consistent comparisons, even if it doesn't represent a physical surface you could stand on. There are also cases where planets are detected directly, not just through their effects on their stars. This is called direct imaging, and it's one of the most challenging techniques in astronomy. To directly image a planet, astronomers have to block out most of the star's light, often using a device called a coronagraph. This creates an artificial eclipse, allowing faint objects nearby to become visible. This method works best for young, massive planets that are far from their stars. These planets are still warm and glowing from their formation, making them easier to see in infrared light. When a planet is directly imaged, its size isn't measured by a simple dip in light. Instead, scientists estimate its brightness and temperature and use models to infer its radius. This approach is less precise than transit measurements, but it provides valuable information, especially for planets that don't transit their stars. Another subtle tool in the measurement toolkit is gravitational microlensing. This technique relies on the way gravity bends light. When a star passes in front of a more distant star, its gravity can act like a lens, magnifying the background star's light. If the foreground star has a planet, that planet can create a small additional blip in the magnification pattern. Microlensing can reveal planets that are far from their stars and even planets that are free-floating, not bound to any star at all. However, it usually provides limited information about size. It's better at telling us about mass and distance than radius, so for the largest planets, the most detailed size measurements usually come from transits, often combined with radial velocity data. But even with these methods, there are uncertainties. Measuring the size of a star is not always straightforward. Stars can vary in brightness, their surfaces can have spots and flares, their distances might not be known with perfect precision. All of these factors can affect the estimate of the planet's size. That's why astronomers often refine their measurements over time. A planet might be discovered with an initial estimate of its radius, and then, as better data comes in, that estimate might be adjusted slightly upward or downward. In some cases, a planet that was once thought to be among the largest might slip down the list as its size is revised. In other cases, a world that didn't seem especially remarkable at first might turn out to be more extreme than anyone realized. There's also the matter of stellar companions. Some stars are actually part of binary systems, with two stars orbiting each other. If this isn't recognized, it can affect the measurements. The light from the second star can dilute the transit signal, making the planet appear smaller than it really is. So part of measuring a planet's size is making sure you understand the entire system it's in, not just the planet itself. Another layer of complexity comes from the shape of the planet. Most size measurements assume the planet is roughly spherical. But as we discussed earlier, rapidly rotating planets can be noticeably flattened at the poles and bulged at the equator. For distant exoplanets, this effect is usually too subtle to detect directly. But in principle, a very fast-spinning, very large planet might appear slightly larger in transit than it would if it were perfectly round. There are even ideas about detecting this kind of flattening by looking at very precise transit light curves, where the shape of the dip might carry information about the planet's outline. This is still an area of active research, but it shows how detailed these measurements can become. When it comes to the largest planets, another important factor is temperature. A hot, inflated atmosphere can make a planet appear larger in optical wavelengths than it does in infrared. This is because different layers of the atmosphere become opaque at different wavelengths. So a planet's measured radius can depend slightly on what kind of light you're using to observe it. This means that size is not always a single, fixed number. It can vary depending on how you look. Astronomers often take this into account by measuring transits at multiple wavelengths and building a more complete picture of the planet's atmospheric structure. This kind of work has been done with space telescopes like Hubble and, more recently, the James Webb Space Telescope. By observing the same planet in different parts of the spectrum, scientists can see how its apparent size changes and infer the presence of clouds, hazes, and different gases. And for some of the largest, puffiest planets, these observations have revealed atmospheres that extend incredibly far from the planet's centre, sometimes to the point where the outer layers are being stripped away by the star's radiation. So in a very real sense, measuring a planet's size is also a way of measuring how it's interacting with its environment. There's also a statistical side to all of this. When astronomers talk about the largest planets, they're often comparing a group of planets that have been measured using similar methods. This helps ensure that the comparisons are fair. A planet measured by direct imaging might not be directly comparable to one measured by transits, because the uncertainties and assumptions are different. So part of the quiet work of planetary science is building catalogues, standardizing measurements, and carefully noting how each value was obtained. This might sound dry, but it's what allows scientists to say with confidence that one planet is larger than another, rather than just guessing based on incomplete information. There's also a sense of humility built into this process. Astronomers are always aware that their measurements are limited by their instruments and their models. They report uncertainties along with their values. A planet's radius might be listed as, say, 1.8 times that of Jupiter, plus or minus a small fraction. Those plus or minus numbers matter. They remind us that what we know is always an approximation. And yet, even with those uncertainties, a pattern emerges. Some planets are clearly much larger than others. Some clearly sit at the upper end of what we've observed so far. So when someone asks, "How do you know this is one of the largest planets ever discovered?" the answer is not a single measurement, but a web of observations. Light curves, spectra, stellar models, follow-up studies, comparisons across many systems. It's a collective effort, built over time, refined as new data comes in. There's something quietly satisfying about that. Worlds of immense scale are revealed through methods that depend on patience and attention to detail. A universe that builds planets the size of small stars is studied through changes in light that can be smaller than the flicker of a candle. As you let this idea settle, you might picture an astronomer watching a graph on a screen, a smooth line of starlight brightness dipping ever so slightly and then rising again. That small dip represents a world passing in front of its star, a world that might be larger than Jupiter, a world that might have an atmosphere stretching thousands of kilometers into space. From that tiny signal, an entire planet enters our understanding. Once you can measure a planet's size and mass, you can start to ask a deeper question. Not just how big is it, but what is it like inside? What is it made of? Why does it have the size and shape that it does? Somewhere in the quiet space between a star's steady glow and the careful attention of astronomers on Earth, a particular kind of question begins to take shape. It's not a loud or urgent question. It doesn't demand an immediate answer. Instead, it lingers, gently persistent, asking what happens when curiosity, technology, and the vastness of the universe meet at a single point of comparison. Out of that meeting comes the idea of a record, the largest planet ever found so far. That phrase, so far, does a lot of quiet work. It carries with it an understanding that what we know today may change tomorrow, that every list and every title is provisional, waiting for the next faint signal from a distant star to rearrange the order of things. Still, within the limits of what we've measured and confirmed, there are a few worlds that stand out as especially wide, especially inflated, especially difficult to ignore. To talk about the largest planet ever found so far, we have to return to the way astronomers usually define largest in this context. It almost always refers to size by radius or diameter, not by mass. The reason is practical. Size is what the transit method measures most directly. When a planet passes in front of its star, the amount of light it blocks tells us how wide it is, at least in terms of where its atmosphere becomes thick enough to stop starlight. Using that definition, the title of largest tends to go to planets that are not just massive, but also highly inflated. These are often gas giants orbiting close to their stars, their atmospheres expanded by intense heat and internal energy. One of the names that frequently appears near the top of these lists is a planet called WASP-17b. WASP-17b was discovered in 2009 as part of the Wide-Angle Search for Planets project, a survey designed to look for transiting planets around bright stars. When astronomers first analysed its data, they noticed something unusual. The dip in the star's light suggested a planet that was extraordinarily wide. Follow-up measurements confirmed it. WASP-17b has a radius nearly twice that of Jupiter. In some estimates, it reaches about 1.9 to 2 times Jupiter's radius, depending on the exact models and measurements used. To put that into a more tangible frame, imagine Jupiter. Now imagine a version of it that stretches nearly twice as far from its centre in every direction. The volume of such a world would be more than 6 times greater than Jupiter's, even if the mass is much lower. It's a planet that takes up an enormous amount of space without containing a proportionate amount of material. That low density is one of its defining features. WASP 17b is often described as one of the puffiest planets known. Its mass is only about half that of Jupiter, yet its size is nearly double. That combination makes it incredibly light for its volume. If you could somehow stand on a solid surface inside this planet, which is a purely hypothetical exercise, the gravity would feel much weaker than Jupiter's, even though the world itself is far larger. The mass is spread out over a much bigger region, so the pull at the outer layers is relatively gentle by giant planet standards. WASP 17b orbits its star at a very close distance, completing a full orbit in just a few days. This proximity exposes it to intense radiation, which heats its atmosphere and keeps it expanded. The planet is also notable for its unusual orbit. It appears to orbit in a direction opposite to the rotation of its star, a retrograde orbit that suggests a turbulent past, possibly involving gravitational interactions with other planets or stars. This combination of extreme size, low density, and odd orbital behaviour makes WASP 17b feel like more than just a record holder. It feels like a case study in how flexible and creative planetary systems can be. Another planet that often enters the conversation is HAT P67b. This world is also remarkably large and even less dense than WASP 17b. It has a radius close to twice that of Jupiter and an incredibly low mass for its size. HAT P67b orbits a star that is larger and hotter than the Sun, and like many of these oversized giants, it sits very close to its star. The heat it receives helps keep its atmosphere in an expanded state. What makes HAT P67b especially interesting is how close it comes to the boundary between planet and something else. Its host star is in a later stage of its life, beginning to expand into a subgiant. As the star grows, it may eventually engulf the planet, ending its existence in a slow, inevitable way. So when we talk about the largest planet ever found so far, we're often talking about worlds that may not be long for the universe in their current form. They're caught in a phase where they are at their biggest, before time and stellar evolution reshape them. There are other candidates as well, planets like TREES 4b, Kepler 12b, and Kelt 11b, each with radii significantly larger than Jupiter's. These worlds all share similar traits. They are close to their stars, they are hot, they are low in density, and they challenge the simple idea that a planet's size should scale neatly with its mass. But here's where the phrase, "ever found so far," becomes especially important. The list of largest planets is not fixed. It changes as new discoveries are made and as existing measurements are refined. For example, a planet might initially be reported as having a radius of 2.1 times that of Jupiter. Later, with better data on the star's size or distance, that estimate might be revised down to 1.9. Another planet might be discovered with an even larger estimated radius, but with larger uncertainties. So astronomers tend to be cautious about declaring a single permanent champion. Instead, they often talk about a small group of planets that occupy the extreme upper end of the size range. There's also a deeper question hiding beneath the surface. Are these planets truly the largest that exist, or just the largest that are easiest for us to find? The transit method favours large planets close to bright stars. These are the ones that create the most noticeable dips in starlight. So our sample of known oversized planets is shaped by our detection techniques. It's possible that there are planets even larger than WASP 17b or HAT PXD7b, orbiting farther from their stars or around dimmer stars, where they are harder to detect. These worlds might not transit from our point of view. They might not cause a large enough wobble in their stars to be easily measured. So the title of largest is not just a statement about the universe, it's also a statement about our tools. That doesn't make these discoveries any less impressive. It just places them within a broader context of ongoing exploration. Another interesting angle is the relationship between size and survival. These extremely inflated planets are often in precarious positions. Their atmospheres are extended and loosely bound, making them vulnerable to being stripped away by their stars. Some of these planets show signs of atmospheric escape. Observations in ultraviolet light have revealed streams of gas trailing behind certain hot Jupiters, like invisible tails. Over long periods of time, this process can significantly reduce the planet's mass and size, so the largest planet ever found so far might represent a temporary state, a moment in a planet's life when it is at its most expanded, before it gradually shrinks or transforms into a smaller, denser world. In that sense, the record holder is not just a static object, it's a snapshot in a long story of change. There's also the question of what lies just beyond the category of planet. As we discussed earlier, objects more massive than about 13 times Jupiter's mass confuse deuterium and are often classified as brown dwarfs. Some of the most massive objects in this range have sizes similar to Jupiter, not much larger. They don't tend to be record holders for diameter, because their strong gravity compresses them. So the largest planets by size tend to be relatively light for their volume, sitting comfortably below the brown dwarf threshold. This creates an interesting contrast. The biggest looking planets are not the heaviest. They are in a way the most delicate giants. There's something quietly poetic about that, even without leaning into metaphor. The worlds that take up the most space are not the ones with the most substance. They are the ones that have found a way to stretch out, to hold on to heat and gas, to occupy a wide region of space with relatively little mass. From a scientific perspective, these planets are valuable because they test the limits of our models. They force scientists to consider how energy moves through a planet's interior, how atmospheres respond to extreme radiation, and how gravity and temperature balance each other. For example, one of the puzzles is why some hot Jupiters are much more inflated than others at similar distances from their stars. There may be differences in their internal structure, their magnetic fields, or their atmospheric circulation that affect how they transport and retain heat. Another possibility is that the presence of heavy elements in the planet's core or atmosphere can influence how efficiently it radiates energy into space. A planet with more heavy elements might cool and contract faster, becoming more compact over time, so the largest planets offer a way to probe these internal processes, even though we can't see inside them directly. There's also a sense in which these worlds serve as bridges between categories. They sit between the familiar gas giants of our solar system and the small stars and brown dwarfs that begin to glow on their own. They show us what happens when you push a planetary system to its extremes without quite crossing over into something fundamentally different. From a human perspective, there's something appealing about having a largest anything. It gives us a point of reference, a way to anchor our imagination. But as you spend time with the details, that anchor starts to feel less like a fixed post and more like a floating marker. It tells you where the edge of your knowledge is, not where the edge of the universe lies. Because beyond WASP-17b, beyond HAT P67b, beyond every name we've written into our catalogues, there are countless stars we haven't studied closely yet. There are regions of the galaxy we haven't surveyed in detail. There are planetary systems that haven't had their light curves plotted or their spectra analysed. Somewhere among those unexamined points of light, there may be worlds that are larger, more inflated, or more extreme than anything we've seen so far. Or it may be that nature really does impose a soft limit, and the planets we've already found are brushing up against it. Either way, the question remains open. It's also worth noticing how these discoveries shape our sense of scale back here on Earth. Thinking about a planet twice the size of Jupiter can make even the largest things in our everyday lives feel small by comparison. Cities, mountains, oceans all become tiny features on a world that itself would be a small dot next to one of these giants. But there's a balance to that thought. These enormous planets, for all their size, are still just parts of larger systems. They orbit stars. Those stars orbit the centres of galaxies, and those galaxies are part of a wider cosmic web, So largest is always relative. It depends on what you're comparing and how far out you zoom. What processes cause a planet's atmosphere to expand into such a wide, diffuse envelope? What keeps it there, and what eventually allows it to shrink back down? Across the long stretch of space between a star's steady glow and the drifting path of a planet, there is a constant exchange of energy that rarely draws attention to itself. It doesn't announce its presence with flashes or sounds. It simply flows, quietly, from one body to another, shaping atmospheres, stirring winds, and, in some cases, causing entire worlds to expand beyond what seems reasonable. This slow, persistent flow is at the heart of why some planets swell until they look more like soft, overfilled shapes than the compact spheres we might expect. To understand this gentle swelling, it helps to start with a simple idea from everyday experience. When you heat something, it usually expands. Air in a balloon spreads out when it gets warm. Metal rails on a hot day grow slightly longer. Even a cup of water will rise just a bit in volume as its temperature increases. The same basic principle applies to planetary atmospheres, but on a scale that stretches across thousands of kilometers. For a gas giant orbiting close to its star, heat is not an occasional visitor. It's a constant companion. The star's light and radiation pour into the upper layers of the planet's atmosphere, warming the gas and giving its particles more energy. As those particles move faster, they push outward, causing the atmosphere to puff up and occupy a larger region of space. This alone can explain some amount of swelling, but it doesn't tell the whole story. If heat from the star were the only factor, then every close-in gas giant would look roughly the same size given similar mass and distance. In reality, they don't. Some planets remain relatively compact, while others balloon outward to astonishing proportions. So astronomers began looking deeper, not just at what's happening on the outside, but at what's going on inside these worlds. One important factor is how a planet handles the energy it receives. When a planet absorbs heat, it doesn't all stay in the atmosphere. Some of it is carried deeper into the interior. The way this energy moves depends on the structure of the planet, its composition, and the motion of its atmosphere. In some planets, strong winds can transport heat from the day side, the side facing the star, to the night side. This circulation can drive energy deeper into the atmosphere, warming layers that would otherwise remain cooler. That deeper heating can cause the planet to expand from the inside out, not just at the surface. Think of it like warming a loaf of bread in an oven. If only the crust gets hot, the loaf doesn't change much overall. But if the heat penetrates deeper, the whole loaf can expand slightly as the air inside warms and spreads. Another source of internal energy comes from the planet's own history. When a giant planet forms, it starts out hot. The process of gathering gas and collapsing under gravity releases energy, and that energy is stored as heat inside the planet. Over time, the planet slowly radiates that heat into space and cools down, which can cause it to contract. But if something interferes with that cooling, the planet can stay larger for longer. One way this can happen is through tidal heating. If a planet's orbit is not perfectly circular, its distance from its star changes slightly as it moves around. The star's gravity pulls on the planet more strongly when it's closer and more weakly when it's farther away. This changing pull can flex the planet's interior, generating heat through friction, much like bending a piece of wire back and forth makes it warm. This process is well known in our own solar system. Jupiter's moon, Io, is heated by tidal forces from Jupiter and the other Galilean moons, and that heat drives its intense volcanic activity. For a close-in giant planet, tidal heating can occur on a much larger scale. If the planet's orbit is slightly stretched, or if it's being influenced by another planet in the system, the resulting internal heating can add to the energy coming from the star. This extra heat can keep the planet's interior warm and its atmosphere expanded. Another layer of complexity comes from the planet's magnetic field. A strong magnetic field can interact with the stellar wind. The stream of charged particles flowing out from the star When these particles collide with the planet's magnetosphere, they can deposit energy into the upper atmosphere. This process is similar in a broad sense to what creates auroras on Earth, but on a giant planet close to a star it can happen on a much larger scale, potentially contributing to the heating and expansion of the atmosphere. Composition also plays a role. Not all gases behave the same way when heated. Some are better at absorbing and trapping energy. If a planet's atmosphere contains certain molecules, they can act like a blanket, holding on to heat and preventing it from escaping easily. Water vapor, carbon compounds, and other heavier molecules can increase the atmosphere's ability to retain energy. This can slow the planet's cooling and help maintain an inflated state. There's also the matter of how the planet's interior is layered. Some models suggest that certain giant planets may have regions where heavier elements are mixed in with lighter gases in ways that affect how heat moves through the planet. If heat has a harder time escaping from the interior, the planet can remain swollen for longer periods. This idea of heat transport is central to understanding why two planets that look similar on the outside can have very different sizes. One might efficiently radiate its internal heat into space and gradually contract. The other might trap that heat, staying larger and puffier. Age, once again, plays a role here. Younger planets are generally hotter and larger. Over time, as they cool, they shrink. So when astronomers observe a particularly inflated planet, one of the questions they ask is whether it's relatively young. But this isn't always enough to explain what they see. Some planets appear to be billions of years old and still remarkably large. That suggests there are ongoing processes keeping them inflated, not just leftover heat from their formation. Another factor to consider is atmospheric escape. This might seem like it would make a planet smaller, not larger, but the process can be more subtle. When the upper layers of a planet's atmosphere are heated by intense radiation, some of the gas can gain enough energy to escape into space. This creates a flow of material away from the planet, sometimes forming a long, invisible tail. This escape process can alter the structure of the atmosphere. It can remove lighter gases from the upper layers, changing the way the remaining atmosphere absorbs and redistributes heat. In some cases, this can lead to a reorganization of the atmospheric layers that temporarily enhances the planet's apparent size in certain wavelengths of light. So even the loss of material can, in a complex way, be part of what makes a planet look swollen when we measure it. It's also worth thinking about the role of clouds and hazes. Many giant planets have thick cloud layers made of compounds that would be exotic on Earth, such as silicates or metal oxides. These clouds can sit high in the atmosphere, blocking starlight at higher altitudes. When astronomers measure the size of a planet using the transit method, they're measuring where the atmosphere becomes opaque to light. If a planet has high-altitude clouds or hazes, that opaque layer can be farther out, making the planet appear larger than it would if the atmosphere were clear. So in some cases, part of a planet's swollen appearance might come from the way light interacts with its atmosphere, not just from the physical expansion of the gas itself. Another piece of the puzzle is the relationship between mass and radius. As we discussed earlier, adding mass to a gas giant doesn't always make it bigger. At some point, the extra gravity compresses the planet, so the planets that tend to look the largest are often those with relatively low mass for their size. They have enough gravity to hold onto a thick atmosphere, but not so much that they squeeze it into a compact shape. This creates a kind of sweet spot for inflation. Planets in this range can puff up dramatically when heated, while more massive planets remain relatively compact even under similar conditions. There's also an interesting feedback loop at work. As a planet's atmosphere expands, the gravity at the outer edge becomes weaker because you're farther from the centre of mass. This can make it easier for the atmosphere to stay extended and even for some of it to escape. That escape can then change the composition and structure of the atmosphere, which can affect how heat is absorbed and retained. So the planet's size, gravity and atmosphere are all tied together in a dynamic balance, each influencing the others over time. Another thing to consider is the star itself. Not all stars are the same. Some are more active, producing strong stellar winds and frequent flares. These can deliver bursts of energy to a planet's atmosphere, heating it and potentially driving changes in its size. Stars also change over time. As a star ages, it can become brighter and larger. A planet that formed at a comfortable distance might find itself exposed to much more intense radiation later in its life, which could trigger or enhance atmospheric inflation. So a planet's swelling is not just about the planet, it's about the ongoing relationship between the planet and its star. There's also a subtle observational angle to all of this. The size we measure for a planet depends on the wavelength of light we're using. Different gases and particles in the atmosphere block different kinds of light at different altitudes. In visible light, a planet might appear a certain size. In infrared, where we're looking at heat rather than reflected light, it might appear slightly smaller or larger, depending on the structure of the atmosphere. By comparing measurements across different wavelengths, astronomers can build a more detailed picture of the planet's atmospheric layers and how far they extend. For some of the most inflated planets, these multi-wavelength observations have revealed atmospheres that stretch so far from the planet's centre that they're only loosely bound by gravity. In these cases, the line between the planet and space becomes especially blurred. This brings us back to the idea of limits. How big can a planet get before it stops being a planet in any meaningful sense? If its atmosphere is constantly flowing away into space, if its outer layers are shaped more by the star's radiation than by the planet's own gravity, at what point does it become something more like a cloud than a world? These are not just philosophical questions. They tie directly into how scientists classify and understand what they observe. From a modelling perspective, explaining planetary inflation has been one of the more challenging problems in exoplanet science. Simple models that include only heating from the star often fall short of reproducing the most extreme cases. That's why researchers continue to explore combinations of effects, tidal heating, magnetic interactions, atmospheric chemistry, and internal structure to see how they might work together. There's also ongoing work to understand how stable these inflated states are. Are they long-lasting, or are they brief phases in a planet's life? Do all close-in gas giants go through a swollen stage, or only some of them? The answers to these questions will shape how we think about the largest planets ever discovered. If inflation is a temporary phase, then the largest planets might simply be those we happen to catch at the right moment. If, on the other hand, some planets can remain inflated for billions of years, then these oversized worlds represent a stable class of giant planets, not just a fleeting curiosity. There's a quiet beauty in how all of this comes together. A planet's size is not just a number, it's the outcome of a long, ongoing conversation between gravity and heat, between formation and environment, between the planet and its star. Every swollen giant carries within it a record of that conversation. In its extended atmosphere, in its low density, in its response to radiation and tides, you can read hints of how it formed, how it moved, and how it has been shaped over time. You might picture one of these inflated planets drifting close to its star, its atmosphere glowing faintly, stretched outward by heat and motion. The star's light washes over it constantly, and the planet responds by expanding, shedding, and reshaping itself in a slow, steady rhythm. At a certain point in the quiet climb from small to large, from light to heavy, from cool to hot, the universe begins to blur one of its own categories. The difference between a planet and a star, which feels so clear when you're looking at Earth and the Sun, becomes much less obvious when you start exploring the massive worlds that sit near the upper end of what we call a planet. Somewhere in that wide, dimly lit region of possibility lives a class of objects that don't fit comfortably into either box. They are not quite planets, they are not quite stars, they are the in-between, and they mark the thin line that challenges how we define what a world really is. To understand this boundary, it helps to start with what makes a star a star. A true star shines because of nuclear fusion. Deep in its core, hydrogen atoms are pressed together under enormous pressure and temperature, merging to form helium and releasing energy in the process. That energy flows outward, eventually reaching the surface and radiating into space as light and heat. This process requires an incredible amount of mass. Gravity must be strong enough to squeeze the star's core to temperatures of millions of degrees. Without that mass, the pressure never gets high enough for fusion to begin, and the object remains dark, at least in terms of generating its own light. Planets, even very large ones, don't reach those conditions. They may be hot inside, they may glow faintly from leftover heat of formation, but they don't have the sustained nuclear reactions that define a star. Between these two categories sits a group of objects known as brown dwarfs. They are sometimes called failed stars, although that name can be a little misleading. It suggests that they tried to become stars and didn't quite make it, when in reality they are simply objects that formed in a way similar to stars but didn't gather enough mass to fully ignite. Brown dwarfs form from collapsing clouds of gas, much like stars do. They don't necessarily form in disks around other stars the way planets do. Instead, they can form on their own, directly from a region of gas that becomes dense enough to collapse under its own gravity. Because of this, brown dwarfs often start their lives hot. They glow in infrared light, radiating the energy from their formation. Over time, they cool and fade, becoming dimmer and harder to detect. There is a particular threshold that often gets used to draw a line between planets and brown dwarfs. That threshold is related to a type of nuclear fusion that involves deuterium. Deuterium is a heavier form of hydrogen. It has one proton and one neutron in its nucleus, rather than just a single proton like ordinary hydrogen. Fusing deuterium requires less extreme conditions than fusing regular hydrogen. It can happen at lower temperatures and pressures. Objects with about 13 times the mass of Jupiter are thought to be massive enough to briefly fuse deuterium in their cores. They don't sustain this process for billions of years the way stars do, but they can do it for a short time early in their lives. So by one common definition, anything above about 13 Jupiter masses is considered a brown dwarf, and anything below is considered a planet. This seems like a neat, tidy rule. But as with many things in astronomy, reality doesn't always stay neatly inside the lines. For one thing, that mass limit isn't exact. The exact threshold for deuterium fusion depends on the object's composition. An object with a slightly different mix of elements might start fusing deuterium at a slightly lower or higher mass. For another, the ability to fuse deuterium doesn't necessarily reflect how the object formed. A very massive planet that formed in a disk around a star could, in theory, cross that 13 Jupiter mass line and briefly fuse deuterium, even though its origin was planetary, not stellar. So you could end up with an object that looks like a planet in terms of its formation history, but behaves like a brown dwarf in terms of its internal physics. This is where the thin line becomes less of a line and more of a zone. There are objects known as super-Jupiters that sit right near this boundary. They have masses several times that of Jupiter. Some are 10, 12, or even 15 times as massive. Depending on how you define things, some of these might be called planets, others might be called brown dwarfs. What makes this especially interesting is that, in terms of size, these objects often look very similar. A super-Jupiter with 10 times Jupiter's mass might have almost the same radius as Jupiter. A brown dwarf with 20 times Jupiter's mass might also have a radius not much different. This happens because as mass increases in this range, gravity compresses the object more and more. The extra material doesn't make it wider, it makes it denser. So you can't easily tell whether something's a planet or a brown dwarf just by looking at how big it is. You need to know how heavy it is, and ideally, how it formed. From an observational standpoint, that's a challenge. It's much easier to measure size than it is to determine formation history. So astronomers often find themselves working with incomplete information. They can measure a planet's radius from transits. They can estimate its mass from stellar wobble. But figuring out whether it formed in a disk or collapsed from a cloud is much harder. In some cases, the environment provides clues. If a massive object is found very close to a star, in a tight planet-like orbit, it's more likely to have formed in a disk. If it's found far away, on a wide star-like orbit, or drifting alone through space, it might be more likely to be a brown dwarf. But these are general trends, not hard rules. There are even objects known as free-floating planets, worlds that don't orbit any star at all. Some of these may have formed in disks and been ejected. Others may have formed more like brown dwarfs. From a distance, they can look very similar. So the thin line between planet and failed star is not just about mass, it's about history, environment, and behaviour. Another piece of this boundary comes from internal structure. Planets that form in disks tend to build up a solid core first, then gather gas around it. Brown dwarfs, forming from collapsing clouds, may be more uniform throughout without a distinct core. If we could look inside these objects, we might be able to tell them apart more easily. But since we can't, we rely on indirect measurements and models. There's also the matter of luminosity. Young brown dwarfs can be quite bright in infrared light, because they're still hot from their formation, and from any deuterium fusion they may have experienced. Massive planets can also be bright when they're young, but they tend to cool and fade more quickly. So in very young systems, it can be especially hard to tell whether a glowing object is a planet or a brown dwarf. This ambiguity becomes particularly relevant when we talk about the largest planets ever found. Some of the most massive objects that get included in these discussions are right at the edge of the brown dwarf category. Depending on how strict you are with definitions, the largest planet might actually be something that another astronomer would call a failed star. This isn't just a semantic issue, it affects how we interpret the object's place in its system. If it's a planet, it likely formed as part of a planetary system, and may have influenced the formation and evolution of other planets around the same star. If it's a brown dwarf, it might be more like a companion star, shaping the system in a different way. So classification matters for understanding the broader story of how systems form and evolve. There's also a cultural side to this boundary. The word planet carries a certain weight in the human imagination. It's just a world, a place, something you might, at least in theory, imagine visiting or standing on. The word star suggests something much more remote, much more powerful, something that defines a system rather than being part of one. Brown dwarfs sit in between these ideas. They are worlds in the sense that they are objects you could orbit. Some of them even have their own planets, but they are also star-like in their formation, and, at least early on, in their behaviour. So when astronomers debate whether a particular object is a planet or a brown dwarf, they're not just sorting things into bins, they're deciding how that object fits into the larger story of the universe. There's a deeper question here about how much our categories reflect reality, and how much they reflect our need for tidy labels. The universe doesn't seem to care about our definitions. It produces objects across a continuous range of masses, sizes, and properties. We draw lines through that range to make sense of it, but those lines are human inventions. That doesn't mean they're useless. On the contrary, they help us organize our knowledge and communicate with one another, but they are always approximations. The thin line between planet and failed star is a reminder of that. From a scientific perspective, this boundary is also a place of opportunity. Objects near this line can tell us a lot about how stars and planets form. By studying their properties, astronomers can test models of disk formation, cloud collapse, and the role of environment in shaping different kinds of objects. For example, if we find a massive object near the brown dwarf boundary in a tight, planet-like orbit, that might suggest that planetary disks can sometimes produce very massive worlds. If we find similar mass objects mostly on wide, star-like orbits, that might suggest that they form more like stars. So these borderline cases become important data points. There's also an interesting connection to the search for the largest planets. The fact that size and mass don't scale neatly in this range means that the largest looking planets are not necessarily the ones closest to this boundary. In fact, as we've seen, the most massive objects tend to be more compact. The puffiest, widest planets are often much lighter, so the largest planets by size are not the ones that are about to become stars. They are in a way at the opposite extreme. They are the most extended, the most diffuse. So the thin line between planet and failed star runs almost perpendicular to the line between small and large in terms of radius. One is about mass and internal physics, the other is about heat, atmosphere and expansion. That creates a kind of cross-shaped landscape of possibilities, where you can have small but heavy objects, large but light ones, and everything in between. As astronomers continue to explore this landscape, they keep refining their tools. New telescopes, more sensitive instruments, and more detailed models allow them to probe these objects in greater depth. The James Webb Space Telescope, for example, is capable of studying the atmospheres of giant exoplanets and brown dwarfs in unprecedented detail. By looking at their chemical makeup, temperature profiles, and cloud structures, scientists can gain insights into how these objects formed and how they differ from one another. Over time, this may help sharpen the boundary, or at least make its nature clearer. But it's also possible that the boundary will remain fuzzy, because the universe itself is fuzzy in this region. There may always be objects that sit comfortably in the grey area, refusing to be easily classified. There's something quietly fitting about that. The most interesting places in science are often the ones where categories break down, where simple rules stop working, and where deeper understanding is required. The thin line between planet and failed star is one of those places. As you let this idea settle, you might picture a massive object drifting through space, glowing faintly with internal heat, orbiting a star or perhaps wandering alone. Is it a planet? Is it a star that never quite ignited? The answer might depend on which part of its story you focus on. And that sense of open-endedness brings us back to the broader theme of this journey. The search for the largest planet is not just about finding something bigger than everything else. It's about exploring the edges of what we know, the places where definitions soften and understanding deepens. Beyond the list of names and numbers that fill astronomy catalogues, there's a quieter, more open-ended kind of question that tends to linger in the background. It doesn't ask for a record or a ranking, it asks about possibility. If we've already found planets that stretch nearly twice the size of Jupiter, if we've seen worlds so puffed up they barely seem held together, then what lies just beyond the edge of what we know? Could there be planets even larger, even more extreme, waiting in parts of the universe we haven't looked closely enough yet? To sit with that question, it helps to step back from individual discoveries and think about the universe as a whole. The galaxy we live in, the Milky Way, contains hundreds of billions of stars, and beyond it there are billions of other galaxies, each with their own stars, their own disks of gas and dust, their own opportunities for planets to form. The number of planetary systems in the observable universe is so large that even conservative estimates start to feel abstract. So when we ask whether larger planets could exist, we're not just asking about a few systems we've studied so far. We're asking about what might be possible across an enormous range of environments, star types, chemical compositions, and histories. One way to approach this is to look at the ingredients. Planet formation depends on three main things: material, time, and conditions. You need a disk of gas and dust around a young star. You need enough time for that material to clump together. And you need conditions that allow a growing world to hold on to what it gathers. If any one of these factors changes, the outcome can change dramatically. Consider material first. Some stars form in regions that are richer in heavy elements than others. Astronomers often refer to this as metallicity, which in this context means the abundance of elements heavier than hydrogen and helium. A disk with more heavy elements can build solid cores more efficiently, which can help form giant planets more quickly. In such environments, it's easier for a core to reach the critical size needed to start pulling in large amounts of gas before the disk dissipates. That opens the door to the formation of very massive, very gas-rich planets. Now imagine a region of space where star formation is especially active, where clouds of gas and dust are dense and rich. In those regions, disks might be larger and more massive than average. A planet forming in such a disk could, in principle, have access to more raw material than the ones we typically observe around nearby stars. More material means more potential for growth. But even with abundant material, there are still physical limits. Gravity, pressure, and temperature shape what a planet can become. As a planet grows more massive, its gravity compresses it. As it becomes hotter, its atmosphere expands. These two effects push against each other. The planets that look the largest by radius tend to be in a sweet spot. They are massive enough to hold onto thick atmospheres, but not so massive that their gravity squeezes them into compact forms. They are hot enough to inflate, but not so hot that they lose their atmospheres entirely. So if we're looking for planets larger than anything we've seen so far, we might expect them to exist in environments that favour this balance. Perhaps they orbit stars that provide steady, intense heat without extreme flares. Perhaps they formed in disks that were just massive enough to build a solid core and then supply large amounts of gas, but not so massive that the planet crossed into the brown dwarf range. There's also the factor of age. Younger planets are often larger. They haven't had time to cool and contract, so if we look at very young star-forming regions, we might find giant planets that are temporarily much larger than their older counterparts. Some of the largest objects found through direct imaging, for example, are young, massive planets orbiting far from their stars. These planets are still glowing with the heat of formation. They appear large and bright in infrared light. As they age, they will cool, dim, and likely shrink. So in a sense, the universe might be full of planets that are, at certain moments in their lives, larger than anything we've catalogued so far, even if they don't stay that way. Another angle to consider is the diversity of stars themselves. Most of the planets we've discovered orbit stars similar to the Sun, or smaller, cooler stars known as red dwarfs. But the universe also contains much larger and more massive stars. Massive stars have stronger gravity, brighter light, and often shorter lifespans. The disks around them can be more massive as well, at least early on. That raises an interesting possibility. Could a very massive star host a planetary disk capable of forming truly enormous planets? There are challenges here. Massive stars emit intense radiation that can blow away the gas in their disks more quickly. That can make it harder for planets to form at all, especially giant ones that need time to gather gas. But if a planet were able to form quickly in such a disk, it might have access to a large reservoir of material. So these environments might be rare, but they could, in principle, produce unusual outcomes. There's also the question of where we look. Most planet hunting missions focus on stars in our relatively local region of the galaxy. These stars tend to have chemical compositions similar to the Sun's, but the Milky Way is not chemically uniform. Different regions have different histories of star formation and element production. The inner parts of the galaxy, closer to the galactic centre, tend to be richer in heavy elements. This is because many generations of stars have lived and died there, seeding the region with heavier materials. In such regions, planetary disks might be especially rich in the solid material needed to build large cores quickly. That could, in theory, increase the chances of forming massive gas giants. The challenge is that these regions are harder to observe. There's a lot of dust and gas between us and the galactic centre, which blocks visible light. Observations in infrared and radio wavelengths can penetrate this dust, but detecting transiting planets or measuring stellar wobbles in such crowded fields is difficult. So it's possible that some of the most extreme planets are hiding in places we haven't been able to study in detail yet. Another possibility comes from thinking about planetary systems that don't look like ours at all. In our solar system, the giant planets are well separated. They orbit at different distances, each with its own space. But in some exoplanet systems, planets are packed much more closely together. There are systems with multiple giant planets in tight orbits, interacting strongly with one another. In such systems, gravitational interactions can lead to dramatic events. Planets can be scattered into new orbits. Some can be ejected from the system entirely. Others can be pushed inward toward the star. A planet that is pushed inward might become a hot, inflated giant, swelling as it absorbs heat. If it started out massive and gas-rich, this process could create a world that appears exceptionally large. So the dynamics of a system, not just its initial conditions, can play a role in creating extreme planets. There's also the concept of free-floating planets, worlds that are not bound to any star. Some of these may have formed in disks and been ejected. Others may have formed more like brown dwarfs directly from collapsing clouds. If a massive free-floating planet exists, especially a young one, it could be quite large and warm. It wouldn't be heated by a star, but it would still be glowing with its own internal heat. These objects are difficult to detect because they don't cause transits or stellar wobbles. They're usually found through microlensing or direct imaging in infrared. So our knowledge of them is still limited. It's possible that some of the largest planetary mass objects in the universe are wandering alone, not orbiting any star, and therefore not easily found by the methods we use most often. Another factor to consider is time itself. The universe has been around for about 13.8 billion years. Over that time, conditions for star and planet formation have changed. In the early universe, there were fewer heavy elements. The first generations of stars formed in an environment dominated by hydrogen and helium. That might have made it harder to form planets with solid cores, and therefore harder to form giant planets. As time went on and more stars lived and died, the universe became richer in heavier elements. That made it easier for planets to form, especially large ones. So there may be an era, perhaps relatively recent on cosmic timescales, where the conditions for forming large gas-rich planets are especially favourable. That suggests that the largest planets might be more common in certain epochs of the universe's history than in others. There's also the role of technology in shaping our answers. Our current telescopes and missions are sensitive to certain kinds of planets in certain kinds of systems. They are particularly good at finding large planets close to their stars. As new instruments come online, especially ones designed to directly image planets or to study faint signals from more distant systems, our view of what exists may change. The James Webb Space Telescope is already pushing into new territory by studying the atmospheres of exoplanets in unprecedented detail. Future missions are planned to directly image Earth-like planets, but along the way they may also reveal new classes of giant planets in wide orbits. Ground-based observatories with extremely large mirrors are also being built. These will have the resolution and sensitivity to study stars and planets in regions of the galaxy that are currently difficult to access. So part of the answer to whether larger planets exist is tied to whether we will be able to find them. There's a subtle distinction here between physical possibility and observational possibility. A planet might exist that is larger than anything we've seen, but if it doesn't transit its star, doesn't cause a strong stellar wobble, and isn't bright enough to be imaged directly, it might remain invisible to us for a very long time. So our current list of largest planets is a list of the largest planets we can see with our current methods. That leaves plenty of room for surprises. Another idea that sometimes enters these discussions is whether truly enormous planets could form in environments very different from typical star systems. For example, in the dense regions of star clusters, where stars pass relatively close to one another, disks can be disrupted, merged, or reshaped. In such environments, material from one disk could be captured by another star, potentially creating unusually massive disks. A planet forming in such a disk might have access to an unusually large supply of gas. These are speculative scenarios, but they highlight how varied the universe can be. The standard picture of a star forming in relative isolation with a neat, tidy disk is not the only possibility. There are also galaxies with very different properties from the Milky Way. Some are rich in gas, some are undergoing bursts of star formation, some have low metallicity, others high. Each of these environments offers a different set of initial conditions for building stars and planets. So when we ask about the largest possible planet, we're really asking about the range of conditions the universe can produce. There's also a conceptual limit that comes from definitions. At some point, an object becomes so massive that calling it a planet becomes awkward, regardless of how it formed. If it can sustain nuclear fusion, even briefly, it starts to behave more like a star. So if we're strict about that boundary, then there is a ceiling on how massive a planet can be. But that ceiling doesn't necessarily limit how large it can appear by radius, because as we've seen, mass and size don't always scale together. So the largest looking planets are often not the most massive. They are the ones that have found a way to spread out, to stay hot, to hold onto a thick atmosphere. That suggests that if even larger planets exist, they might be in the same general category. Hot, low-density, gas-rich worlds in close orbits, or young, glowing giants still cooling from their formation. There's also the question of whether we might eventually find planets that are, say, 3 times the radius of Jupiter. Most models suggest that this would be very difficult to sustain. At that size, the atmosphere would be extremely loosely bound, and escape rates might be very high. But the universe has a habit of finding ways around our expectations. Maybe there are combinations of mass, composition, and heating that allow for more extreme inflation than we currently understand. Maybe there are atmospheric processes that can maintain extended envelopes more efficiently. Or maybe the planets we've already found are brushing up against the true limits, and what we'll discover next is not something bigger, but a clearer understanding of why things stop where they do. Either outcome would be valuable. From a human perspective, there's something calming about holding this question open. It reminds us that our knowledge is a work in progress, that the universe is not something we've finished exploring. Every new planet discovered, especially one that stretches the boundaries of what we thought was possible, adds another piece to a puzzle that may never be fully complete. As you sit with the idea of these possible worlds, you might imagine a distant star far beyond the reach of our current surveys. Around it, perhaps, a planet larger than any we've catalogued so far moves in a slow, steady orbit. Its atmosphere might be glowing with heat, or drifting outward into space. Its existence might be marked only by a tiny regular dimming of its star's light that no one has noticed yet. That thought doesn't demand an answer. It simply invites a sense of openness. From the moment we begin to compare our small familiar world with the vast, distant giants that circle other stars, a subtle shift takes place in how the universe feels. It stops being a backdrop and starts becoming a kind of story, one that unfolds through patterns, limits, and quiet hints about how everything fits together. The largest planets we've found so far are not just impressive because of their size. They are meaningful because of what they reveal about how the universe builds things, how it changes them over time, and how much room there still is for surprise. When astronomers study these giant worlds, they aren't only trying to understand the planets themselves, they're using them as tools, as markers that point toward deeper processes. A very large planet carries within it a record of the environment it formed in. Its mass, its composition, its orbit and its size are all shaped by the disk of gas and dust that once surrounded its star, by the chemistry of that material, and by the gravitational interactions that followed. So in a sense, each giant planet is like a fossil. Not a fossil of a living creature, but of a formative era, a time when a young star system was still in motion, still deciding what it would become. One of the first things these giants tell us is that the universe does not favour a single blueprint. For a long time, our own solar system was the only example we had. Rocky planets close to the sun, gas giants farther out, everything in relatively calm circular orbits. It felt orderly, almost designed. Then came the hot Jupiters, the super puffs, the massive worlds in tight, fast orbits that didn't fit the pattern at all. Their existence showed that the layout of our system is not a universal rule. It's one outcome among many. This realization changes how we think about planet formation. Instead of a single, predictable process, we now see a range of possibilities. Some systems build giants early and let them migrate inward. Others keep them far out. Some never build giants at all. Others build several. The giants, especially the largest ones, sit at the extremes of this range. They show us what happens when conditions push planetary growth toward its upper limits. Another thing these worlds reveal is how strongly stars and planets are linked. A planet's size and structure are not just the result of what it gathers during formation. They are also shaped by what its star does to it over time. When we look at an inflated giant planet, we're often seeing the long-term effect of radiation, stellar wind, and gravitational interaction. The star heats the planet. The planet responds by expanding. The star's gravity pulls on the planet. The planet responds by flexing and heating internally. This ongoing exchange turns the star and planet into a kind of coupled system, where changes in one can lead to changes in the other. That idea extends beyond individual systems. It suggests that the properties of planets across the galaxy are tied in a broad way to the properties of their stars. The mass of the star, its temperature, its age, and its chemical makeup all influence what kinds of planets form and how they evolve. By studying large planets around different types of stars, astronomers can begin to map out these relationships. They can ask questions like whether larger stars tend to host larger planets, or whether stars with more heavy elements are more likely to produce gas giants. The answers to these questions help build a picture of how common different kinds of worlds might be in the universe. There's also something to be learned from where these giants are found. The fact that many of the largest looking planets are close to their stars tells us that migration is a common process. Planets don't always stay where they're born. They move. This movement reshapes entire systems. A giant planet moving inward can clear out material, scatter smaller planets, or change the orbits of worlds that remain. So the presence of a large planet in a tight orbit hints at a more dramatic past, a time when the system was more crowded and more chaotic. That history matters when we think about the broader question of habitable environments. The path a giant planet takes through a system can influence whether smaller, rocky planets end up in stable, life-friendly orbits or are pushed into inhospitable regions. So in an indirect way, the study of these giant worlds connects to the search for life elsewhere. They are not just objects of interest in their own right. They're actors in the larger drama of planetary systems. Another message these planets send is about the behaviour of matter under extreme conditions. Inside a giant planet, pressures and temperatures reach levels far beyond what we can recreate in laboratories on Earth. Hydrogen becomes metallic. Electrons move freely. Materials take on properties that don't exist under everyday conditions. By modelling these interiors and comparing predictions with observations, scientists can test theories about how matter behaves when it's squeezed and heated to such extremes. This has implications that go beyond planetary science. It touches on physics more broadly, on how elements and compounds behave in environments that are rare in our corner of the universe but common elsewhere. So a large planet becomes a kind of natural experiment, one that the universe is running continuously and that we are trying to observe from a distance. There's also a lesson here about time. The giants we see today are not necessarily the giants that will exist tomorrow, or that existed in the past. Planets change, they cool, they lose atmosphere, they migrate, their stars change too, growing brighter or fainter, more active or more stable. So when we study a large planet, we're seeing a moment in a long story. That moment is shaped by billions of years of prior events, and will, in turn, shape what comes next. This perspective encourages a kind of patience in how we think about the universe. It reminds us that what we observe is always a snapshot, not a final state. Another thing these worlds tell us is how much our own understanding depends on our tools. The fact that we've found so many large, close-in planets is partly because those are the easiest to detect. So the universe we see through our data is not a perfect mirror of the universe that exists. It's filtered by our methods. The giants highlight this bias. They show up clearly in our surveys. Smaller, more distant planets are harder to find. So the current picture of planetary populations is weighted towards certain kinds of worlds. Recognizing this helps scientists design better instruments and missions, It shapes where they look and how they interpret what they find. There's also a broader, almost philosophical message in all of this. The existence of planets so much larger than our own challenges our sense of what is normal. On Earth, we tend to measure things in human terms. A large building, a wide river, a long journey. These scales make sense in our daily lives. But when you start thinking about a planet that could hold thousands of Earths inside it, those everyday measures lose their meaning. The giants force us to adopt a different frame of reference. They push us to think in terms of planetary scales, stellar scales, and galactic scales. That shift can be strangely calming. It places our own concerns in a wider context. It reminds us that we are part of a much larger system, one that has been unfolding for billions of years and will continue long after we're gone. Another insight these worlds offer is about diversity. Not just the diversity of planets, but the diversity of outcomes in general. The same basic ingredients, gas, dust, gravity, and time, can produce rocky worlds like Earth, ringed giants like Saturn, puffed up super-Jupiters, and faint brown dwarfs. The differences come from subtle variations in conditions and timing. This suggests that the universe is not fine-tuned to produce one particular kind of world. It is capable of producing many across a wide range of possibilities. That idea carries over into how we think about life and habitability. If the universe can build such a wide variety of planets, it may also be capable of supporting a wide variety of environments. The giants themselves may not be friendly to life as we know it, but their moons, their influence on systems, and their role in shaping planetary architectures can create conditions where smaller, more temperate worlds can exist. So in a roundabout way, the study of large planets contributes to the broader question of whether we are alone in the universe. There's also a practical side to this knowledge. Understanding how giant planets form and evolve can help scientists interpret observations of young star systems, disks, and stellar environments. For example, when astronomers observe a disk with a gap in it, they might infer that a large planet is forming or has already formed there, carving out that space. By understanding what kinds of planets can create such features, they can better understand what they're seeing. So the giants become part of a toolkit for studying not just planets, but the broader process of star and system formation. Another message these worlds carry is about limits. We often think of the universe as boundless, and in many ways it is. But the behaviour of large planets shows that there are constraints. Gravity, pressure, temperature, and nuclear physics all impose boundaries on what is possible. You can't make a planet arbitrarily massive without turning it into something else. You can't make a planet arbitrarily large without running into problems with atmospheric escape or structural stability. So the largest planets we find are not just curiosities. They are signposts that mark where one set of physical rules gives way to another. In that sense, they help map the edges of planetary space, the region of possibility where planets exist and beyond which stars begin. This idea of edges and boundaries is a recurring theme in science. We learn a lot by studying the extremes, the hottest stars, the coldest regions of space, the largest planets, the smallest particles. These extremes test our theories. They reveal where our understanding works and where it needs to be refined. So the giants serve a similar role. They sit at the edge of what we consider planetary, and by doing so, they help sharpen our understanding of what a planet is. There's also an emotional dimension to this, even in a calm, reflective way. Thinking about these worlds can inspire a sense of wonder that doesn't rely on drama or spectacle. It comes from the quiet realization that the universe is capable of building things on scales we can barely imagine, and that we, small as we are, have found ways to notice and study them. This connection between the very small and the very large is part of what makes astronomy feel special. A tiny change in a star's brightness, measured by a sensitive instrument on a distant planet, can reveal the presence of a world that dwarfs everything we know. So the giants tell us something about ourselves too. They tell us that curiosity and careful observation can bridge enormous distances. They tell us that understanding doesn't always require proximity. Sometimes it just requires patience. The picture that emerges is not just of a universe filled with big planets, but of a universe filled with patterns, processes, and possibilities. The largest planets are like punctuation marks in that larger story. They don't define the whole narrative, but they draw attention to important moments, important transitions, important questions. Here, after wandering through distant systems and enormous worlds that stretch the idea of planet to its edges, the focus begins to soften and slowly turn back towards something closer, something familiar. The journey outward has been about size, mass, heat, and gravity, about numbers that grow so large they almost lose their meaning. But the journey back carries a different kind of weight. It's about what those distant giants quietly do to the way we think about our own small place in the universe. When you look at Earth from the surface, everything feels large enough. The sky seems endless. The ocean feels boundless. Mountains look immovable. Distances stretch into hours, days, or weeks of travel. In the scale of everyday life, our world is already vast. Then you learn about a planet that could hold 1,000 Earths inside it, and that sense of scale gently shifts. It doesn't erase the importance of what's close, it reframes it. The idea of a giant planet, swollen and glowing near its star, drifting through space, as part of a system so far away that its light takes centuries or millennia to reach us, adds a quiet layer of perspective to the ordinary. It reminds us that the universe is not built around what feels large to us. It's built around rules and processes that operate across ranges of size and time that we can only partly imagine. And yet, all of our understanding of those distant worlds comes from this one. From a small rocky planet orbiting a medium-sized star in a fairly ordinary part of a fairly ordinary galaxy. That fact alone carries a kind of quiet symmetry. The smallest and the largest are connected by the same act of looking. One of the things these giant planets do, almost without trying, is challenge the idea that importance is tied to size. A world can be massive, wide, and powerful in terms of gravity, and still be, in a sense, empty. A gas giant has no solid surface to stand on, no place where a human story could unfold in the way it does here. Earth, by comparison, is small. But it's dense with detail. It's layered with oceans, forests, cities, and histories. Its surface is active, changing, shaped by weather, life, and time. So when you hold the idea of a super Jupiter and the idea of Earth in the same thought, something interesting happens. The contrast doesn't make Earth feel insignificant. It makes it feel specific. It highlights the fact that our world is not just one more object in a catalogue. It's the place where catalogues are made. There's also something grounding about the way planetary science circles back to this point again and again. We study distant worlds to understand how planets form, how they evolve, and how they interact with their stars, and in doing so, we learn more about how our own planet came to be. The giant planets in our solar system, for example, likely played a role in shaping Earth's history. Jupiter's gravity may have influenced the delivery of water and other materials to the inner planets. It may have deflected or redirected comets and asteroids, changing the impact environment in which life eventually emerged. So even here, on this small world, the presence of a giant has mattered. When you extend that idea to other systems, it becomes clear that every planet, large or small, exists as part of a network of influences. A supersized planet close to its star can reshape the entire system. It can clear out material, shift orbits, and determine which smaller worlds survive and where they end up. So the giants and the small worlds are not separate stories. They're chapters in the same, larger process. Another gentle realization that often comes with thinking about these extremes is how much of the universe operates outside the range of our direct experience. We live in a narrow band of temperatures, pressures, and timescales. Step too far outside that band and things become unfamiliar very quickly. The interiors of giant planets are places where hydrogen behaves like a metal. Their atmospheres host winds that move faster than anything on Earth. Their magnetic fields can stretch millions of kilometers into space. These are not environments we can ever visit or fully recreate. And yet, through observation and modelling, we build mental pictures of them. We use math, physics, and imagination guided by data to extend our understanding into places we will never physically go. That act itself is a kind of quiet achievement. It's a reminder that exploration is not limited to travel. It can happen through thought, through careful measurement, through a willingness to follow small clues to large conclusions. There's also a subtle comfort in the idea that, for all the variety and scale in the universe, the same basic rules apply everywhere. Gravity works the same way on Earth as it does around a super Jupiter. Light behaves the same way here as it does around a distant star. The difference is not in the rules, it's in how they play out when you change the conditions. That continuity creates a sense of connection. The planet we stand on and the largest planet we've discovered are part of the same physical story. They're shaped by the same forces, even if those forces express themselves very differently in each case. When you let that idea settle, it becomes easier to see our own world as part of a much wider pattern, rather than as something isolated or separate. There's also something quietly humbling about the way these discoveries are made. The largest planets in the universe are not found by building bigger and bigger machines and reaching out to touch them. They're found by noticing very small things, a dip in a light curve, a shift in a spectrum, a pattern in a stream of data. From those subtle signs, entire worlds are revealed. That contrast between the scale of what is discovered and the scale of the signal that reveals it speaks to a kind of balance in the way knowledge grows. Big ideas often rest on small observations, and those observations in turn depend on patience. Astronomy is not a science of quick answers, it's a science of long watching. Stars change slowly. Orbits repeat over days, months, or years. Data accumulates bit by bit. So when a new, oversized planet is confirmed, it's often the result of years of work by many people, each contributing a piece to the picture. That collaborative, gradual process is another way the study of giant worlds reflects something human. It shows how understanding is built collectively, over time, rather than all at once. There's also a kind of quiet continuity between the ancient and the modern in this field. For thousands of years, people have looked up at the sky and noticed the bright wandering points of light that we now know are planets. Jupiter was one of those points. Today, we look at stars that are too faint to see with the naked eye, and notice even fainter changes in their light. From that, we infer the presence of worlds far beyond anything ancient observers could have imagined. And yet, the basic act is the same. Looking up, noticing patterns, wondering what they mean. The scale of the universe hasn't changed. Our tools and our interpretations have. Thinking about the largest planets also brings up the idea of limits in a more personal sense. It reminds us that there are things we may never fully know. We can measure, model, and observe, but there will always be details beyond our reach. That's not a failure. It's part of what keeps exploration open-ended. Every time we find a new kind of world or push a boundary a little farther, we also create new questions. Why does this planet look the way it does? How long will it stay that way? What does its existence imply about the systems we haven't seen yet? So the story doesn't really end with a list of the largest planets. It continues with a set of possibilities. From a more grounded point of view, there's something reassuring about returning to Earth after thinking about such vast things. The planet beneath our feet is not the largest, not the most massive, not the most extreme, but it is for us the most meaningful. It's the place where the sky is something you can step outside and look at. Where the light from distant stars and planets reaches an eye, a camera, or a sensor. Where questions turn into conversations and then into careful studies. So in a way, every discovery about a distant giant is also a discovery about this small world. It's a reminder that we are part of a universe that is both understandable and endlessly complex. The giants tell us about scale. Earth tells us about experience. The two together create a fuller picture. As this reflection settles, the sense that remains is not one of finality, but of continuity. The universe doesn't present itself as a finished story. It presents itself as an ongoing one. New stars are forming. New planets are taking shape. Light is travelling across space from places we haven't yet studied. Somewhere out there, perhaps, a planet larger than any we've found so far is quietly orbiting its star, its presence marked by a faint regular dimming that no one has noticed yet. And here, on a small, active and attentive world, instruments are being built, surveys are being planned, and people are still looking up. So the path between the largest worlds and the smallest remains open. It's a path made of curiosity, patience, and the steady flow of light across space. And as long as that light keeps reaching us, and as long as there are eyes and minds ready to notice its subtle changes, the story of planets, both giant and small, will continue to unfold gently without a final page.